The Cretaceous era lasted from about 145 million to 66 million years ago. It was the final period of the Age of Dinosaurs and one of the most important chapters in Earth's history. During this time, continents continued to separate, and shallow seas covered large parts of the land. The climate was generally warm, and there were no permanent ice caps at the poles. Flowering plants appeared and spread widely, changing ecosystems. Dinosaurs such as Tyrannosaurus and Triceratops lived on land, while large marine reptiles occupied the oceans. So what makes the Cretaceous era one of the most important periods in Earth's history? Around 145 million years ago, Earth moved gently from one chapter of its history into another. There was no sunrise that looked different from the day before, no thunderclap to announce the change. Yet deep within layers of rock, in tiny differences in fossils, and in the slow shifting of continents, a new geological period had begun. This was the start of the Cretaceous, the last and longest chapter of the Age of Dinosaurs. By the time this period began, our planet was already unimaginably old. Life had first appeared billions of years earlier in simple, microscopic forms. Over time, that life had grown more complex. Plants had colonized the land, insects had filled the air, amphibians and reptiles had explored rivers and forests. The Age of Dinosaurs had already been underway for tens of millions of years. The Cretaceous did not begin life from scratch. Instead, it inherited a world that was alive, restless, and constantly changing. Millions of years earlier, nearly all of Earth's land had been joined together in one enormous supercontinent called Pangaea. This giant landmass stretched from pole to pole and was surrounded by a vast global ocean. But Pangaea did not remain whole. Heat from deep inside the planet pushed upward, cracking the crust and pulling the land apart. By the time the Cretaceous began, Pangaea had already split into two major pieces. The northern landmass was known as Laurasia, and the southern one was called Gondwana. Even these two enormous continents were not stable. They were breaking apart into smaller sections, drifting slowly but steadily across the surface of the globe. North America was separating from Europe and Africa. South America was beginning to pull away from Africa, opening a growing gap between them. India was breaking free from the southern lands and beginning a long northward journey that would eventually lead it to crash into Asia many millions of years later. Australia and Antarctica were still joined together, forming a large southern landmass that was far warmer than the icy continent we know today. As these continents drifted, new oceans were forming. The early Atlantic Ocean was narrow and young, more like a long sea than the wide ocean we recognize now. Between the northern and southern continents stretched the warm and expansive Tethys Ocean. This ocean acted like a giant tropical belt around the planet, spreading warm water and influencing global climate. The climate at the start of the Cretaceous was warm almost everywhere. There were no massive ice sheets at the poles. Antarctica was not buried under kilometers of ice. Instead, it supported forests and rivers. Fossil evidence shows that dinosaurs and other animals lived there comfortably. Even regions close to the poles experienced milder conditions than today. One reason for this warmth was the high level of carbon dioxide in the atmosphere. Volcanoes were active as continents split apart, releasing gases that trapped heat. The spreading ocean floor also played a role. When new ocean crust forms at underwater ridges, it pushes older crust upward. This causes sea levels to rise. With no polar ice caps to lock away water, the oceans expanded over low-lying land. Shallow inland seas covered large portions of continents. In what is now the middle of North America, a vast body of water spread across the land at different times during the Cretaceous. At the very beginning of the period, rising seas were already reshaping coastlines. The world map looked strange and unfamiliar. Coastlines were curved and jagged in ways we would not recognize. Islands dotted wide tropical waters. The oceans themselves were alive with extraordinary creatures. Ammonites, with their spiral shells, drifted through the water in enormous numbers. They came in many shapes and sizes, some small and delicate, others large and heavily armored. These animals were close relatives of modern squid and octopus. Their fossils are so common that they serve as important markers for dating rock layers. Large marine reptiles ruled the seas. Ichthyosaurs, shaped somewhat like modern dolphins but entirely reptilian, were swift hunters. Plesiosaurs, with long necks and paddle-like limbs, glided through warm waters in search of fish. Some marine reptiles had shorter necks and massive jaws filled with sharp teeth. Coastal waters may have echoed with splashes as these predators pursued their prey. Sharks were already ancient by this time and were thriving. Early forms swam in both shallow and deep waters. Bony fish were diversifying, developing new shapes and feeding strategies. Coral reefs flourished in warm, sunlit waters. These reefs were not only beautiful structures but also complex ecosystems filled with countless species. On land, plant life painted the continents in shades of green. At the very beginning of the Cretaceous, flowering plants had not yet become dominant. Forests were still ruled by conifers, which resembled modern pine trees. Cycads, with thick trunks and crown-like leaves, grew in abundance. Ferns formed dense undergrowth in moist regions. Ginkgo trees, with fan-shaped leaves, added to the diversity. The air in many regions would have been humid and heavy with plant scents. Rain fell regularly in tropical zones, feeding rivers that carried sediment toward the seas. In other areas, climates may have been more seasonal, with periods of dryness followed by heavy rains. Because the continents were arranged differently, ocean currents flowed along unusual paths, distributing heat in ways that kept even high latitudes relatively warm. Dinosaurs were the most visible and powerful animals on land. By the start of the Cretaceous, they had already diversified into many groups. Giant plant-eaters walked slowly across plains and through forests. Some had long necks that allowed them to reach high into treetops. Others had heavy bodies protected by armor plates and spikes. Meat-eating dinosaurs varied from small, fast hunters to larger predators. Although the most famous giant predators would appear later in the Cretaceous, their ancestors were already present. Some carnivorous dinosaurs were developing feathers. These feathers may have helped with insulation or display. Birds had already evolved from small feathered dinosaurs during the earlier Jurassic period, and during the Cretaceous they would continue to spread and diversify. The skies were far from empty. Pterosaurs, the flying reptiles, soared above coastlines and forests. Some were no larger than birds. Others were enormous, with wingspans stretching wider than small aircraft. They nested along cliffs and hunted fish in shallow waters. Their silhouettes would have been a common sight against the bright Cretaceous sky. Mammals also lived during this time, though they were small and not dominant. Many were nocturnal, hiding from dinosaurs during the day. They likely fed on insects, seeds, and small animals. Their existence might seem minor compared to towering dinosaurs, but they were quietly evolving traits that would later allow their descendants to take over the planet. Beneath all of this surface life, the Earth itself remained active. Tectonic plates continued their slow movement. Volcanoes erupted along spreading ridges and continental rifts. Earthquakes shook regions where plates collided or pulled apart. Mountains rose in some places and began eroding in others. The beginning of the Cretaceous was not marked by a single catastrophic event. Unlike the dramatic asteroid impact that would later end the period, the transition from the Jurassic to the Cretaceous was gradual. Scientists identify the boundary by studying tiny fossils in marine rock layers. Certain species disappear while new ones appear. These small biological changes signal the turning of geological time. One of the most important long-term developments that began early in the Cretaceous was the rise of flowering plants. At first, they were rare and limited in distribution. They grew quietly among the dominant conifers and ferns, but they possessed a powerful innovation: flowers that attracted insects for pollination and seeds enclosed within protective fruits. These features allowed them to reproduce efficiently and spread into new environments. As flowering plants expanded, they formed new ecological relationships with insects. Early pollinators evolved to feed on nectar and pollen. This partnership would eventually reshape terrestrial ecosystems. Forests would change in appearance. Food sources for herbivores would diversify. The world was slowly moving toward a more modern style of plant life. Imagine standing on a coastal plain at the beginning of the Cretaceous. The air is warm, perhaps warmer than most places on Earth today. In the distance, conifer forests stretch toward the horizon. A shallow sea glimmers nearby, filled with life beneath its surface. Pterosaurs circle overhead. The ground trembles faintly as a herd of large plant-eating dinosaurs moves through the trees. Insects buzz around ancient plants. The sky is bright and clouds drift slowly above a world that feels both familiar and alien. Time during the Cretaceous moved as it always does, day by day, season by season. Yet over millions of years, the slow drift of continents reshaped coastlines. The Atlantic Ocean widened steadily. South America and Africa grew farther apart. India continued its long northward voyage. These changes would eventually alter ocean currents and climate patterns even more. The early Cretaceous laid the groundwork for the dramatic events that would unfold later in the period. Dinosaur diversity would reach extraordinary heights. Flowering plants would spread across the globe. Marine life would continue to evolve in complex ways. And eventually, after tens of millions of years, the period would end in one of the most famous mass extinctions in Earth's history. But at its beginning, the Cretaceous was a world of warmth, growth, and steady change. It was a time when Earth's surface was being reshaped by deep forces. Oceans were expanding, continents were drifting, forests were evolving, dinosaurs ruled with confidence, unaware that their dominance would one day end. In that distant age, there were no humans to observe or record what was happening. No cities, no machines, no written words, only wind in the trees, waves along ancient shores, and the steady heartbeat of a living planet moving forward through time. The beginning of the Cretaceous was not loud or sudden. It was the quiet opening of a long and remarkable chapter in Earth's story, a chapter that would shape the world in ways still visible today. More than 200 million years ago, long before there were cities, countries, oceans filled with ships, or even humans to imagine such things, the surface of the Earth looked completely different. All the land we know today, Africa, Asia, Europe, North America, South America, Australia, and Antarctica, was once joined together as one enormous supercontinent. Scientists call this ancient giant landmass Pangaea. Its name means all lands, and that is exactly what it was. One vast stretch of rock and soil surrounded by a single enormous ocean. At the time Pangaea existed, life on Earth was very different. Dinosaurs had begun to appear, strange reptile-like creatures roamed the land, and the first small mammals were only just beginning their long story. Plants were spreading across the continents, forming forests in some regions and dry deserts in others. Because all the land was joined together, animals could walk from one end of the supercontinent to the other without crossing an ocean. There were no wide seas separating populations. This allowed many species to spread far and wide. But Pangaea did not last forever. The Earth beneath it was restless. Deep inside our planet, the mantle, a thick layer of hot, slowly moving rock, was constantly shifting. The outer shell of the Earth, called the crust, is not one solid piece. It is broken into large slabs called tectonic plates. These plates float on the semi-molten mantle below them. Over very long periods of time, they move. Sometimes they collide, sometimes they pull apart, sometimes they slide past one another. The story of the breaking apart of Pangaea begins when these plates started to stretch and crack the giant landmass. Around 200 million years ago, in what scientists call the early part of the Mesozoic era, cracks began forming within Pangaea. At first, these were small fractures, but over time they grew wider and deeper. Molten rock from beneath the crust pushed upward into these cracks. As it cooled, it created new crust. Slowly, almost too slowly to imagine, the supercontinent began to tear itself apart. The first major split divided Pangaea into two enormous pieces. The northern half became known as Laurasia, and the southern half became Gondwana. Laurasia would eventually give rise to North America, Europe, and much of Asia. Gondwana would eventually become South America, Africa, Antarctica, Australia, and the Indian subcontinent. Between these two huge land masses, a new ocean began to form. This ocean would later become part of what we now call the Atlantic. The creation of new oceans was one of the most dramatic parts of Pangaea's breakup. When tectonic plates pull apart, the space between them fills with molten rock that rises from the mantle. As this rock cools, it forms new oceanic crust. This process is known as seafloor spreading. Over millions of years, the gap widens, and an ocean basin grows larger and larger. What begins as a narrow rift valley can eventually become a vast ocean separating entire continents. One of the earliest signs of Pangaea's splitting can still be seen today. If you look at the coastlines of South America and Africa, you can see how well they fit together. It is as though they were once joined and later pulled apart. This observation was one of the clues that led scientists to develop the theory of continental drift. In the early 20th century, a German scientist named Alfred Wegener suggested that continents had once been joined together and later drifted apart. At first, many scientists doubted him, but as more evidence was discovered, such as matching fossils on different continents and similar rock formations separated by oceans, his idea gained support. As Laurasia and Gondwana continued to drift apart, they did not remain whole for long. Gondwana itself began to break into smaller pieces. Africa and South America slowly separated from each other. Antarctica and Australia drifted away in their own directions. India, once attached to the southern landmass, broke free and began a long journey northward across the ocean. Millions of years later, India would crash into Asia, pushing up the mighty Himalayas. Meanwhile, in the north, Laurasia also divided. North America began to move away from Europe. The Atlantic Ocean widened between them. The land that would become Greenland shifted position. Over time, Europe and Asia remained joined together, forming the large landmass we now call Eurasia. As these changes unfolded, the face of the planet transformed. New coastlines formed, mountains rose where plates collided, volcanoes erupted along the edges of separating continents, earthquakes shook the land. The breakup of Pangaea was not a gentle or quiet event. It was a dramatic reshaping of the planet, though it happened over tens of millions of years. The changing positions of the continents also changed the climate. When Pangaea was whole, much of its interior was far from the ocean. This meant the center of the supercontinent was often dry and hot, similar to large deserts today. But as the continents split and oceans formed between them, more coastline appeared. Ocean currents began to flow in new patterns. These currents carry heat around the planet, helping to shape climate. As they changed, so did rainfall patterns, temperatures, and wind systems. This shift in climate had a powerful effect on life. As continents drifted into new positions, some moving toward the poles, others toward the equator, the plants and animals living on them had to adapt. Some species could not survive the changes and went extinct. Others evolved in new ways. When land masses separated, populations of the same species became isolated from each other. Over long periods of time, these isolated groups developed into entirely new species. This process helped create the rich diversity of life we see today. The widening of the Atlantic Ocean was one of the most important consequences of Pangaea's breakup. What began as a narrow rift between North America and Africa grew into a vast ocean basin. Today, the Atlantic continues to widen by a few centimeters each year. Deep beneath its waters lies the Mid-Atlantic Ridge, a long underwater mountain range where new crust is still being formed as plates pull apart. While the Atlantic was growing, other oceans were shrinking. The Pacific Ocean, for example, is bordered by regions where plates collide and sink beneath one another in a process called subduction. This means that while some parts of Earth's surface are spreading apart, others are being pushed together. The planet's surface is constantly being recycled in a slow but powerful cycle. India's journey is one of the most fascinating chapters in this story. After breaking away from Gondwana, it drifted northward at a relatively fast pace in geological terms. Eventually, it collided with Asia. The force of this collision was so immense that it crumpled the crust, pushing it upward to form the Himalayan mountain range. Even today, the Himalayas continue to rise slowly as India presses against Asia. Antarctica followed a different path. It drifted toward the South Pole. As it moved into colder latitudes, ice sheets began to form. Eventually, Antarctica became the frozen continent we know today. Australia, once connected to Antarctica, moved northward into warmer waters, developing its own unique ecosystems filled with strange and remarkable animals. Africa moved northward as well, slowly closing the gap between itself and Europe. The Mediterranean Sea is a remnant of an ancient ocean that once lay between these land masses. The movements of Africa and Europe continue today, causing earthquakes in the region and shaping the landscapes of countries around the Mediterranean. North America drifted westward and slightly northward. Along its western edge, collisions with other plates formed mountain ranges such as the Rockies. These geological events were part of the larger pattern of plate movements set in motion during and after the breakup of Pangaea. All of this happened so slowly that no single human lifetime could ever notice the change. Continents move at about the same speed that fingernails grow. Yet over millions of years, this tiny movement adds up to thousands of kilometers. Entire oceans can open. Mountains can rise and erode away. Land that was once near the equator can end up near the poles. The evidence for Pangaea's breakup is found in many places. Geologists study rock layers that match across continents now separated by oceans. Fossils of identical ancient creatures have been discovered in South America and Africa, proving those lands were once connected. Patterns of magnetic minerals in ocean floor rocks show how new crust formed and spread outward from mid-ocean ridges. Even the distribution of earthquakes and volcanoes today traces the boundaries of moving plates. The story of Pangaea reminds us that the Earth is alive in a geological sense. Its surface is not fixed or permanent. It changes, reshapes itself, and builds new features over vast stretches of time. What we see today, the continents and oceans arranged as they are, is only a temporary stage in a much longer story. In the distant future, the continents may once again come together to form a new supercontinent. Scientists have proposed different ideas about what this future landmass might look like. Some suggest the Atlantic could close as plates change direction. Others imagine a new ocean forming elsewhere. Just as Pangaea formed from earlier continents long before it and then broke apart, the cycle may continue. The breaking apart of Pangaea was one of the most important events in Earth's history. It shaped the geography of our world. It influenced climate patterns. It guided the evolution of life. It determined where oceans would flow and where mountains would rise. Without it, the world map would look completely different. The countries, ecosystems, and even human civilizations we know today depend on the ancient movements of tectonic plates that began tearing Pangaea apart over 200 million years ago. Imagine a world without vast sheets of ice at the top and bottom of the planet. Imagine forests stretching into regions that today are locked in darkness and freezing temperatures for much of the year. Envision warm, shallow seas covering large parts of the continents, filled with strange marine reptiles and glittering schools of fish. This was Earth during the Cretaceous, a time that began about 145 million years ago and ended about 66 million years ago. For nearly 80 million years, the planet existed in a powerful greenhouse state, far warmer than today, with little or no permanent polar ice. The Cretaceous climate stands out in Earth's history because of its intense and long-lasting warmth. Today, we live in what scientists call an icehouse world. Large ice sheets cover Antarctica and Greenland. Snow and sea ice form each winter in the Arctic. Temperatures at the poles remain below freezing for much of the year. But during the Cretaceous, this icy picture simply did not exist. Instead of frozen deserts, the poles supported forests, rivers, and even dinosaurs. The idea that crocodile-like reptiles once lived near the Arctic Circle may sound unbelievable, yet fossil evidence confirms exactly that. One of the most important reasons for this warmth was the high level of carbon dioxide in the atmosphere. Carbon dioxide is a greenhouse gas. That means it traps heat. When sunlight reaches Earth, some of it is reflected back into space, but much of it is absorbed by land and ocean. The surface then releases heat back upward. Greenhouse gases absorb some of this outgoing heat and send part of it back toward the surface. This process keeps the planet warmer than it would be otherwise. During the Cretaceous, carbon dioxide levels were likely several times higher than today. Some scientific estimates suggest levels may have been 3, 4, or even 5 times greater at certain points in the period. Why was there so much carbon dioxide in the air? The answer lies deep beneath the surface of the planet. The Cretaceous was a time of intense geological activity. The continents were moving apart. The giant landmass known as Pangaea had already begun to break into pieces, and those pieces continued to drift. North America was separating from Europe. South America was pulling away from Africa. India was racing northward on its long journey toward Asia. As these land masses moved, new ocean crust formed between them along mid-ocean ridges. This process released enormous amounts of volcanic gases, including carbon dioxide. Underwater volcanoes stretched like scars across the ocean floor. On land, volcanic eruptions added even more gases to the sky. Over millions of years, these emissions built up in the atmosphere. The carbon dioxide did not simply disappear. It accumulated, strengthening the greenhouse effect and warming the planet steadily. The arrangement of continents during the Cretaceous also helped shape the climate. Today, the placement of land masses affects how ocean currents move. Ocean currents act like giant conveyor belts, carrying warm water from the equator toward the poles and cold water back toward the tropics. In the modern world, certain continental arrangements create strong temperature contrasts between equator and pole. But during the Cretaceous, the positions of continents allowed warm water to circulate more freely into high latitudes. This helped keep polar regions much milder than they are today. Sea levels were also dramatically higher. In some parts of the Cretaceous, sea levels were hundreds of feet above present levels. Large areas of land were flooded by shallow inland seas. One of the most famous examples was a vast seaway that once split North America into 2 land masses. These shallow seas played an important role in spreading warmth. Water can store heat more effectively than land. Because it warms and cools slowly, it smooths out temperature extremes. With so much shallow ocean water spread across the continents, seasonal differences were likely less extreme in many places. Another powerful factor in maintaining warmth was the absence of large ice sheets. Ice reflects sunlight very effectively. This reflectivity is known as albedo. When sunlight strikes ice and snow, much of it bounces back into space. But when ice is absent, darker surfaces such as ocean water and vegetation absorb more sunlight. This absorbed energy turns into heat, During the Cretaceous, with little or no permanent ice at the poles, the Earth absorbed more solar energy overall. This created a feedback loop. More warmth prevented ice from forming, and the lack of ice allowed even more warming. Fossil discoveries provide vivid proof of this warm polar climate. Scientists have found remains of turtles and crocodile-like reptiles in regions that today lie within the Arctic Circle. These animals cannot survive in freezing environments. Their fossils show that polar regions must have been warm enough to support them year-round, or at least free from long periods of extreme cold. Fossilized tree trunks found in high-latitude locations reveal that forests once grew there. Some of these trees show growth rings, indicating seasonal light changes, yet the climate remained mild enough for continuous forest life. It is important to remember that polar regions still experienced months of darkness during winter. The tilt of Earth's axis has not changed dramatically since that time. So how could forests and animals survive long, dark winters? The answer lies in the overall warmth of the planet. Even without sunlight for part of the year, temperatures likely remained above freezing because the atmosphere retained so much heat. Oceans that had absorbed warmth during summer would slowly release it during winter, preventing extreme cold. The oceans themselves were warmer from top to bottom. Today, deep ocean waters are cold because they form near the poles where surface water cools, becomes dense, and sinks. This process drives global ocean circulation, but in a greenhouse world with little polar cooling, deep water formation may have been weaker or different. As a result, the deep ocean during the Cretaceous was significantly warmer than it is today. Chemical clues locked inside microscopic marine fossils suggest that deep ocean temperatures may have been several degrees warmer, perhaps by as much as 10 degrees Celsius in certain regions. High temperatures influenced life in dramatic ways. Coral reefs flourished in warm, shallow seas. Marine reptiles grew to enormous sizes. On land, dense forests covered large areas, including places that are now dry or cold. The Cretaceous also saw the rapid rise of flowering plants, which began to spread widely and reshape ecosystems. Warm temperatures and abundant carbon dioxide likely encouraged strong plant growth. These lush landscapes provided food for vast numbers of herbivorous dinosaurs, which in turn supported powerful predators. The carbon cycle, which moves carbon between the atmosphere, oceans, rocks, and living things, played a long-term role in maintaining the greenhouse state. Over very long periods, carbon dioxide is removed from the atmosphere when rainwater reacts with rocks in a process called weathering. This carbon eventually ends up in ocean sediments. However, during the Cretaceous, the rate of volcanic emissions and seafloor spreading may have been high enough to balance or exceed this removal. In simple terms, the planet was releasing carbon dioxide as fast as, or faster than, it could be locked away. Antarctica during the Cretaceous looked nothing like the frozen continent we see today. It was not yet isolated by the powerful ocean current that now circles it and keeps it cold. Because of this, warm ocean water could flow more easily around southern high latitudes. Fossil evidence suggests that Antarctica supported forests and diverse ecosystems. The image of a green Antarctica filled with plants and possibly small dinosaurs is a striking reminder of how different Earth can be under greenhouse conditions. Sea levels remained high throughout much of the period because there were no large ice sheets locking up water. When ice melts, water returns to the oceans. In a world without permanent polar ice, more water remained in liquid form, raising sea levels. High sea levels reshaped coastlines. Shallow seas created rich marine habitats and buried vast amounts of organic material. Over millions of years, some of this buried material would transform into fossil fuels such as oil and gas. The Cretaceous climate was not perfectly stable. There were fluctuations. Some intervals were warmer than others. There were also events known as oceanic anoxic events, when parts of the ocean became depleted of oxygen. These episodes were linked to high temperatures and changes in ocean circulation. They sometimes led to marine extinctions. Even in a greenhouse world, climate could shift and ecosystems could suffer. Another fascinating point is that the sun was slightly less bright during the Cretaceous than it is today. Over billions of years, the sun gradually becomes more luminous. Yet despite receiving slightly less solar energy, Earth was much warmer. This highlights the strength of greenhouse gases in controlling climate. High carbon dioxide levels were powerful enough to override the slightly weaker sunlight. As the Cretaceous approached its end around 66 million years ago, the planet was still generally warm. The period concluded with a massive asteroid impact that contributed to the extinction of the dinosaurs and many other species. The immediate aftermath likely caused short-term cooling as dust and debris blocked sunlight. But the long-lasting warmth that defined most of the Cretaceous was the result of slow geological and atmospheric processes operating over tens of millions of years. The greenhouse world of the Cretaceous teaches an important lesson. Earth's climate system is capable of existing in very different states. It can swing between icehouse periods, marked by large polar ice sheets and cooler temperatures, and greenhouse periods, marked by warmth and little or no permanent ice. These transitions take millions of years and are influenced by tectonic movements, volcanic activity, greenhouse gases, and ocean circulation. In the Cretaceous, the combination of high carbon dioxide levels, active seafloor spreading, warm ocean currents reaching high latitudes, elevated sea levels, and the absence of reflective ice created a self-reinforcing cycle of warmth. Forests grew near the poles. Crocodile-like reptiles swam in high-latitude rivers. Deep oceans were warmer, coastlines were flooded. The world was vibrant, lush, and dramatically different from today. Imagining such a planet forces us to rethink what is normal for Earth. The icy poles we know are not permanent features in geological time. They are part of a climate phase that can change. The Cretaceous stands as one of the clearest examples of a greenhouse world, a time when the planet operated without polar ice caps and with global temperatures far above modern averages. It remains one of the most powerful natural laboratories for understanding how greenhouse gases, continents, oceans, and sunlight combine to shape the climate of our world. Rising sea levels have shaped the story of our planet in powerful and sometimes dramatic ways. Long before humans built cities, wrote books, or sailed across oceans, the seas themselves were on the move. At certain moments in Earth's deep history, the oceans rose so high that they flooded large parts of entire continents. Dry land disappeared beneath the waves. Vast forests were drowned. Mountains became islands. And in many places, shallow inland seas formed, stretching for hundreds or even thousands of miles across what had once been solid ground. Sea level is simply the average height of the ocean's surface. But that average can change over time. When sea levels rise, the ocean spreads over land that was once dry. When sea levels fall, land that was once underwater becomes exposed again. One of the main reasons sea levels rise is because of melting ice. During cold periods in Earth's history, huge ice sheets covered large parts of the continents. These ice sheets stored enormous amounts of water. When the climate warmed, the ice melted, and all that water flowed into the oceans. As a result, sea levels rose. Another reason sea levels rise is because water expands when it warms. Warm water takes up more space than cold water, so when global temperatures increase, the oceans swell. Even if no new water is added, the sea can rise simply because it grows larger as it heats up. Over hundreds of millions of years, sea levels have risen and fallen many times. Some of these changes were small, others were enormous. There were periods in Earth's ancient past when sea levels were so high that much of the land we know today was underwater. One of the most dramatic examples happened during the time of the dinosaurs, especially during the Cretaceous period, which began around 145 million years ago and ended about 66 million years ago. During this time, global temperatures were much warmer than they are today. There were no large ice sheets at the poles. Without massive glaciers locking away water, the oceans held more liquid water and sea levels were far higher. In what is now North America, a vast inland sea once stretched from the Arctic Ocean down to the Gulf of Mexico. This body of water is known as the Western Interior Seaway. It divided the continent into two large land masses, like an enormous river of salt water cutting the land in half. Imagine standing in what is now Kansas, Nebraska, or Alberta, and instead of seeing fields and forests, you would see a wide, shallow sea filled with marine life. The Western Interior Seaway was not deep like today's open oceans. In many places it was shallow enough that sunlight reached the bottom. This allowed sea plants and tiny organisms to thrive. Fish, marine reptiles, and strange creatures swam through its waters. Giant predators like mosasaurs hunted there. Flying reptiles known as pterosaurs soared above it. On the shores, dinosaurs walked along sandy beaches that are now found as layers of rock far inland. The rocks formed at the bottom of that shallow sea tell a powerful story. Over time, mud, sand, and the shells of tiny sea creatures settled to the sea floor. These layers hardened into stone. Today, when geologists dig into the ground in the middle of North America, they find fossils of sea creatures in places that are now hundreds of miles from the nearest ocean. These fossils prove that the land was once underwater, but North America was not alone. During times of high sea levels, many other continents were partly flooded as well. Large areas of Europe were covered by shallow seas. Africa had wide coastal waters reaching deep inland. Parts of Asia were submerged. Even areas that are now deserts were once underwater. These shallow inland seas were very different from the deep oceans. Because they were shallow, they were often warm. Sunlight could easily reach the bottom, which encouraged life to flourish. Coral reefs grew, shellfish thrived, tiny plankton filled the waters. These seas became rich ecosystems. When these inland seas later disappeared as sea levels fell, they left behind important natural resources. The remains of ancient marine life sometimes formed thick layers of limestone and chalk. In some places, the buildup of organic material eventually turned into oil and natural gas over millions of years. Much of the fossil fuel humans use today was formed in ancient seas that no longer exist. Sea levels did not remain high forever. Earth's climate continued to change. As temperatures dropped in later periods, ice sheets returned. During the Ice Ages, which began about 2,600,000 years ago, enormous glaciers covered large parts of North America, Europe, and Asia. These glaciers locked up so much water that global sea levels fell dramatically. In some periods, sea levels were more than 100 meters lower than they are today. When sea levels dropped, land bridges appeared between continents. For example, a land bridge once connected Siberia and Alaska, allowing animals and early humans to travel between Asia and North America. This land bridge existed because so much water was frozen in ice sheets that the oceans were lower. Then, as the climate warmed again at the end of the last ice age around 11,700 years ago, the glaciers melted. Sea levels began to rise once more. Coastlines shifted inland. Areas that had been dry land for thousands of years were flooded. The rising waters created new seas, bays, and estuaries. One dramatic example is the area now covered by the North Sea between Britain and mainland Europe. Thousands of years ago, during the last ice age, this region was dry land. It was home to animals like mammoths and to early human hunters. As the ice melted and sea levels rose, this land slowly disappeared beneath the water. Today, fishermen sometimes pull up bones and ancient tools from the sea floor, reminders of a lost world. Rising sea levels have also reshaped the Mediterranean region many times in Earth's history. In some ancient periods, sea levels were so high that coastlines extended far inland. In others, sea levels dropped, and parts of the Mediterranean nearly dried up due to geological changes. Throughout Earth's deep past, the height of the sea has been closely linked to the movement of tectonic plates. The continents sit on giant slabs of rock that float on the semi-molten layer beneath them. These plates move slowly over millions of years. When plates pull apart at mid-ocean ridges, new ocean crust is created. At times when seafloor spreading is rapid, the ocean basins can become shallower because the newly formed crust is warm and buoyant. This can push sea levels higher. During certain periods in the distant past, such as the mid-Cretaceous, rapid seafloor spreading may have contributed to some of the highest sea levels in Earth's history. Scientists believe that during these times, sea levels may have been more than 100 meters higher than they are today. If we could look at a map of Earth from that time, the continents would appear smaller and the oceans would cover far more of the planet's surface. Shallow inland seas were not just temporary pools of water. Some lasted for millions of years. They became stable parts of the landscape. Rivers flowed into them. Storms stirred their waters. Life evolved within them. When sea levels were high for long periods, entire generations of plants and animals adapted to living near these seas. The flooding of continents also had powerful effects on climate. Large, shallow seas can influence temperature and weather patterns. Because water heats and cools more slowly than land, regions near inland seas often had milder climates. Moist air from these seas could travel inland, bringing rain and supporting lush vegetation. In some cases, the rise of sea levels may have contributed to major biological changes. When land was divided by inland seas, populations of animals became separated. Over time, these isolated groups could evolve into new species. The presence of the western interior seaway, for example, may have influenced the evolution of different dinosaur species on either side of the water. The story of rising sea levels is not only about ancient times. Even in the relatively recent past, small changes in sea level have had big effects. Coastal cities, islands, and low-lying areas are especially sensitive to even modest increases in sea level. When the ocean rises, it does not simply cover beaches. It can also push saltwater into rivers and underground water supplies. It can increase the power of storm surges during hurricanes and cyclones. Today, scientists measure sea levels carefully using satellites, tide gauges, and other instruments. They have observed that global sea levels have been rising over the past century. This modern rise is linked to warming temperatures, melting glaciers, and the expansion of seawater as it heats up. However, when we compare today's changes to those in Earth's distant past, we see that our planet has experienced much larger shifts before. Entire continents have been partly drowned. Vast shallow seas have appeared and disappeared. The Earth has never been static. Still, what makes today's situation different is the speed of change and the presence of human civilizations along coastlines. In ancient times, when sea levels rose over thousands or millions of years, ecosystems had more time to adjust. Today, many changes are happening within decades or centuries, which can make adaptation more difficult. If we imagine the future, we can picture how rising sea levels might once again reshape the continents. Low-lying regions could become shallow seas. River deltas could flood. Coastal plains might disappear underwater. New bays and inlets could form. The geological record shows that shallow inland seas are a natural part of Earth's long-term cycle. When conditions are right, the ocean moves inland. When conditions change, it retreats. This cycle has repeated again and again over hundreds of millions of years. Looking at the rocks beneath our feet can be like reading pages from an ancient book. Layers of marine fossils far from the sea tell us that the ocean once stood there. Fine-grained sediments reveal quiet waters. Ripple marks frozen in stone show where waves once moved sand along a shallow sea floor. In many regions, people live and farm on land that was once covered by ancient seas. The fertile soils of some plains were formed from marine sediments. Chalk cliffs in places like southern England are made from the tiny shells of marine organisms that lived in ancient shallow seas. When we study rising sea levels and the creation of inland seas, we are really studying change itself. The Earth has changed dramatically over time. Continents have broken apart and collided. Mountains have risen and worn away. Seas have advanced and retreated. The idea that large parts of continents could be flooded might seem frightening, but in Earth's history, it has been normal. What seems permanent to us is temporary on geological timescales. Coastlines are not fixed lines on a map. They are shifting boundaries between land and sea. In the distant past, if you stood on a hilltop, you might have seen a vast, shallow sea stretching to the horizon where today there is dry land. Fish and marine reptiles would have swum where cattle now graze. Coral reefs might have grown where cities now stand. Rising sea levels have repeatedly reshaped the face of the planet, carving new coastlines and creating shallow inland seas that supported rich and diverse life. They have buried forests, formed fossil fuels, influenced evolution, and left lasting marks in the rocks. By studying these ancient events, scientists gain insight into how Earth's systems work and how they might respond to changes in the future. The story of rising sea levels is a reminder that our planet is dynamic and powerful. The oceans have always had the ability to transform the world's geography in profound ways. More than 100 million years ago, during a time when dinosaurs ruled the land and strange reptiles swam through warm oceans, North America looked nothing like it does today. There were no familiar borders, no highways stretching from coast to coast, no endless plains of wheat or corn. Instead, at the very heart of the continent, a vast body of water shimmered under a subtropical sun. This enormous sea was known as the Western Interior Seaway, and for millions of years it split North America into two separate land masses and transformed the entire region into a world of waves, reefs, swamps, and strange marine creatures. To imagine this ancient sea, you must first picture Earth during the Cretaceous period. The climate was much warmer than it is today. There were no polar ice caps. Sea levels were far higher. In fact, the oceans had risen so much that they flooded low-lying parts of many continents. North America, which we now see as one solid piece of land stretching from Canada to Mexico, was once divided down the middle by this shallow but incredibly wide sea. On the west side lay a landmass called Laramidia. On the east side was another landmass called Appalachia. Between them stretched hundreds of miles of warm, shallow water. The Western Interior Seaway did not appear overnight. Its story began around 100 million years ago, when powerful forces beneath Earth's crust were slowly reshaping the surface of the planet. To the west, tectonic plates were colliding. The oceanic plate, known as the Farallon Plate, was being pushed beneath the North American plate. This process, called subduction, caused the land to buckle and rise, forming mountains in what would later become part of the Rocky Mountains. But while mountains rose in some places, other areas sank. Large parts of the continent's interior slowly dipped downward, creating a broad, shallow basin. At the same time, global sea levels were rising. The climate was warm, and much of Earth's water was not locked away in ice. As the land sank and the oceans rose, seawater began creeping inland from the north and south. From the north, water poured in from the Arctic Ocean. From the south, it pushed upward from the Gulf of Mexico. Eventually, these waters met in the middle of the continent. What began as scattered shallow seas and flooded lowlands merged into one enormous inland sea. At its greatest extent, the Western Interior Seaway stretched from what is now the Arctic Ocean all the way down to the Gulf of Mexico. It covered parts of present-day Canada and the central United States, including areas that would one day become states such as Texas, Kansas, Colorado, Wyoming, Montana, North Dakota, South Dakota, and Nebraska. In some places, it was several hundred miles wide, yet it was not especially deep. In many regions, it was shallow enough that sunlight could easily reach the seafloor. This allowed marine plants and plankton to flourish. Because it was shallow and warm, the sea became one of the richest marine ecosystems in Earth's history. The water teemed with life. Giant marine reptiles swam through its depths. Among them were long-necked plesiosaurs, powerful mosasaurs with jaws full of sharp teeth, and fast-swimming ichthyosaurs shaped like dolphins. Some of these creatures grew to astonishing sizes. Mosasaurs, for example, could reach lengths of more than 50 feet. They were top predators, ruling the waters much like sharks do today. The Western Interior Seaway was also home to enormous fish. One of the most famous was Xiphactinus, a fierce predator that could grow longer than a small bus. Fossils have been found of Xiphactinus with other fish still inside its stomach, preserved in stone as if frozen in time. Another remarkable fish was the armored and powerful Encodus, often nicknamed the saber-toothed herring because of its long fang-like teeth. Above the water, flying reptiles known as pterosaurs soared through the sky. Some had wingspans as wide as small airplanes. They glided over the waves, diving down to snatch fish from the surface. Early birds also appeared during this time, sharing the skies with these reptilian flyers. Beneath the waves, the seafloor was covered in strange and beautiful life. Ammonites, relatives of modern squid and octopus, drifted and swam in the water. Their spiral shells came in many shapes and sizes. Some were small enough to fit in your hand. Others were as large as a car tire. When they died, their shells sank to the bottom, eventually becoming fossils. Today, these coiled shells are some of the most common and recognizable fossils found in rocks from this ancient sea. The seaway also supported massive populations of plankton. Tiny floating organisms drifted in the sunlit waters. When they died, their microscopic shells rained down to the seafloor, forming thick layers of sediment. Over millions of years, these layers were compressed into chalk and limestone. In fact, the famous White Cliffs of Dover in England were formed from similar plankton deposits. In North America, large chalk formations in places like Kansas are direct evidence of the Western Interior Seaway's existence. Life on land changed dramatically because of the sea's presence. On either side of the seaway, dinosaurs evolved separately. Since the inland sea cut the continent in two, species on Laramidia and Appalachia were isolated from each other. This separation led to different types of dinosaurs developing on each side. On Laramidia, which included what is now the western United States, some of the most famous dinosaurs evolved, including Tyrannosaurus rex, Triceratops, and Edmontosaurus. These animals roamed coastal plains, river deltas, and lush forests that bordered the sea. On Appalachia, the eastern landmass, dinosaur fossils are rarer, partly because much of that land has been eroded away or remains buried. However, evidence suggests that different kinds of hadrosaurs and carnivorous dinosaurs lived there. The isolation caused by the sea may have led to unique evolutionary paths. Much like islands today produce unusual species found nowhere else. The coastline of the Western Interior Seaway was constantly shifting. Rivers carried sediment from the rising mountains in the west and deposited it into the sea. Storms churned the shallow waters. Tides moved sand and mud back and forth. In some places, thick swamps formed along the shore. In others, sandy beaches and barrier islands developed. The landscape was alive and ever-changing. During certain periods, oxygen levels in the deeper waters dropped dramatically. Scientists believe that warm temperatures and high nutrient levels led to massive blooms of plankton. When these organisms died and sank, their decay used up oxygen in the water. This created dead zones where many marine animals could not survive. These events are recorded in dark layers of shale rock, which formed under low oxygen conditions. Such rocks are important today because they often contain oil and natural gas, formed from the buried remains of ancient life. The Western Interior Seaway existed for tens of millions of years. However, it was not permanent. Around 70 million years ago, tectonic forces began to change the continent once again. The mountains in the west continued to rise during a period known as the Laramide orogeny. As the land rose, the basin that held the sea began to shrink. At the same time, global sea levels started to fall. Gradually, the waters retreated. The northern and southern connections closed. What had once been an enormous inland sea became smaller and smaller, turning into isolated lakes and marshes. Eventually, the seaway disappeared entirely, leaving behind a transformed continent. The two land masses of Laramidia and Appalachia were reunited into a single North America once again. But although the water vanished, its legacy remained. The sediments it left behind shaped the Great Plains. The fossil-rich rocks of Kansas, Montana, Alberta, and other regions preserve the story of its ancient life. The oil and gas resources found in parts of the central United States are partly the result of organic material buried beneath its waters. Even the fertile soils of some regions owe their existence to sediments laid down in this ancient sea. The story of the Western Interior Seaway also helps scientists understand how climate change can reshape the planet. It shows how rising sea levels can flood vast areas of land. It reveals how ecosystems respond to warm temperatures and changing oxygen levels. It demonstrates how isolation can drive evolution, and it reminds us that continents are not fixed or permanent in their current form. If you could stand in what is now the middle of Kansas during the height of the Western Interior Seaway, you would not see fields of wheat stretching to the horizon. Instead, you would see waves rolling under a bright sky. You might spot the dark shape of a mosasaur gliding beneath the surface. A pterosaur might pass overhead, its wings casting a fleeting shadow on the water. The air would be warm and humid. The shoreline might be miles away. The thought that such a sea once covered the heart of North America can feel almost unbelievable. Yet the rocks beneath our feet tell the story clearly. Fossilized shells, teeth, bones, and microscopic remains provide evidence of a world long gone. Geologists read these rocks like pages in a book, uncovering details about water depth, temperature, and life forms that lived there. The Western Interior Seaway was more than just a body of water. It was a powerful force that reshaped landscapes, divided species, created new habitats, and left lasting marks on geology and biology. It existed during a dynamic chapter of Earth's history, when the planet was warmer, sea levels were higher, and life was both strange and spectacular. In the grand timeline of Earth's history, the Western Interior Seaway lasted only a brief moment, yet its impact was enormous. It reminds us that the continents we know today are the result of constant change. Mountains rise and erode, seas advance and retreat, species evolve and disappear. The planet is always in motion, even if the changes are too slow for us to notice in a single lifetime. The inland sea that once split North America in two was a world unto itself, filled with predators and prey, storms and calm waters, life and death. It shaped the destiny of dinosaurs and left treasures for scientists millions of years later. The Age of Dinosaurs at its peak. When most people imagine dinosaurs, they are not picturing the earliest ones that first appeared millions of years before. They are not thinking of small, lightly built reptiles quietly testing their place in a dangerous and changing world. Instead, they picture giants. They imagine enormous long-necked plant-eaters stretching higher than trees, and terrifying meat-eaters with jaws full of blade-like teeth. They see thick forests, strange flowering plants, and skies filled with flying reptiles. In truth, most of these images belong to one special chapter in Earth's history, the Cretaceous period. The Cretaceous was the final chapter of the long dinosaur era, and it was also the most spectacular. It began about 145 million years ago and ended about 66 million years ago. During this vast stretch of time, dinosaurs reached heights of power, variety, and size that had never been seen before. They spread across nearly every corner of the planet. They ruled the land without serious competition from other large animals. They evolved into forms so strange and so specialized that even today they seem almost unbelievable. Dinosaurs first appeared during the Triassic period, over 230 million years ago. At that time, the world was very different. All the continents were joined together in a single massive landmass called Pangaea. The climate was often hot and dry, and life was still recovering from a devastating mass extinction that had wiped out many earlier species. The first dinosaurs were small and not especially dominant. They shared the land with other reptiles, some of which were just as powerful. During the Jurassic period that followed, dinosaurs began to grow larger and more widespread. Famous giants like Brachiosaurus and the fearsome predator Allosaurus lived during this time. The Jurassic was a time of expansion and growth. Yet even then, dinosaurs were still experimenting with body shapes and survival strategies. They had not yet reached the astonishing diversity that would later define the Cretaceous. By the time the Cretaceous began, the world itself was changing in dramatic ways. The giant supercontinent Pangaea had already started to break apart. Slowly but steadily, the land masses drifted away from each other, forming separate continents that would eventually resemble those we know today. As these continents moved, new coastlines formed. Shallow seas flooded parts of the land. Mountain ranges rose and climates shifted. These changes created new habitats everywhere. There were lush forests, vast plains, swampy lowlands, and warm coastal regions. Each of these environments offered new opportunities for life. Dinosaurs responded to these changes with incredible creativity. In the Cretaceous, they did not merely survive, they flourished. They evolved into countless species, each suited to its environment. Some grew to unimaginable sizes, while others became small and swift. Some developed armor and horns, others developed sharp claws or powerful beaks. The variety was astonishing. One of the most famous creatures of this time was Tyrannosaurus rex. Though it lived near the very end of the Cretaceous, it represents the peak of predatory power among land animals. With a massive skull, teeth as long as bananas, and a bite strong enough to crush bone, it stood as a symbol of dominance. It was not merely large, it was perfectly built for its role. Its strong legs allowed it to move with surprising speed. Its keen senses helped it locate prey. Everything about it was designed for survival at the top of the food chain. But Tyrannosaurus rex was only one of many remarkable predators. Across the Cretaceous world lived other terrifying hunters. There was Spinosaurus, which may have been even longer than Tyrannosaurus rex and had a sail-like structure on its back. It likely hunted fish in rivers and coastal areas, showing how dinosaurs adapted even to semi-aquatic lifestyles. There were also the swift and intelligent dromaeosaurs, sometimes called raptors, which hunted in packs and used curved claws to bring down prey. These smaller predators showed that success did not depend only on size. Strategy, speed, and cooperation also mattered. Plant-eating dinosaurs were just as impressive. The long-necked sauropods continued into the Cretaceous, and some of them reached extreme sizes. Argentinosaurus, which lived in what is now South America, may have weighed as much as several large elephants combined. Its long neck allowed it to reach leaves high above the ground, while its massive body protected it from most predators. Creatures like this were among the largest land animals that have ever lived. Other plant eaters evolved in different directions. Triceratops, with its 3 horns and large bony frill, became one of the most recognizable dinosaurs in history. Its horns were not only weapons against predators, but may also have been used in battles with members of its own species. Then there were the hadrosaurs, often called duck-billed dinosaurs. These animals were highly successful and widespread. Some had elaborate crests on their heads, which may have been used to produce sounds, helping them communicate across long distances. They traveled in herds, suggesting complex social behavior. During the Cretaceous, armored dinosaurs also reached their peak. Ankylosaurus, covered in thick bony plates and armed with a heavy tail club, was like a living tank. Predators would have found it extremely difficult to attack such a well-protected animal. The presence of these defensive adaptations shows how intense the evolutionary competition had become. Predators were becoming more powerful, and prey species responded with stronger defenses. The skies of the Cretaceous were no less dramatic. Although flying reptiles called pterosaurs had appeared earlier, they reached impressive sizes during this period. Quetzalcoatlus, one of the largest known flying animals of all time, had a wingspan as wide as a small airplane. It soared over the land, scanning for food. Meanwhile, true birds were evolving from small feathered dinosaurs. Creatures like Archaeopteryx had appeared earlier, but in the Cretaceous, birds began to diversify more fully. Feathers, which may have first evolved for warmth or display, became essential for flight. The oceans were also filled with powerful reptiles. Though not dinosaurs themselves, creatures like Mosasaurus and Plesiosaurs ruled the seas. The Cretaceous world was truly an age of reptiles in every environment. Land, sea, and sky were dominated by these remarkable animals. Another important reason the Cretaceous was the golden age of dinosaurs was the explosion of plant life, especially flowering plants. Before this time, most plants were ferns, cycads, and conifers. But during the Cretaceous, flowering plants began to spread rapidly. This botanical revolution changed ecosystems everywhere. Flowering plants offered new types of food, including fruits and seeds. Plant-eating dinosaurs adapted to these changes, evolving new ways to chew and digest tougher vegetation. In turn, predators evolved to hunt the plant-eaters. The web of life grew more complex and more interconnected. Climate also played a role in dinosaur dominance. For much of the Cretaceous, the Earth was warmer than it is today. There were no permanent ice caps at the poles. Sea levels were high, and shallow seas covered large parts of continents. Warm temperatures allowed life to thrive in regions that are now cold and barren. Even near the poles, forests grew, and dinosaurs roamed in areas that would today be covered in snow and ice. Dinosaurs during this time were not merely large reptiles wandering aimlessly. Evidence suggests many of them had advanced behaviors. Fossils show nesting sites where adults cared for their young. Some species likely lived in organized groups. There is evidence of migration, suggesting they traveled long distances in search of food. These behaviors added to their success. The Cretaceous also saw a growing separation of continents. As the land masses drifted farther apart, populations of dinosaurs became isolated from one another. This isolation encouraged evolution. On separate continents, different species developed unique features. In what is now South America, enormous titanosaurs evolved. In North America, horned dinosaurs flourished. In Asia, feathered dinosaurs and early birds diversified. Each continent became a laboratory of evolution, producing its own strange and wonderful forms. This long period of dominance lasted tens of millions of years. For an almost unimaginable stretch of time, dinosaurs faced no serious challenge from mammals. Mammals did exist during the Cretaceous, but they were small and mostly active at night. They lived in the shadows, avoiding the giant reptiles that ruled the day. Dinosaurs occupied the large animal roles in ecosystems. They were the grazers, the hunters, the scavengers, and the giants. Yet even at its peak, the Golden Age carried the seeds of its end. Near the close of the Cretaceous, about 66 million years ago, a catastrophic event changed everything. A massive asteroid struck the Earth near what is now the Yucatan Peninsula in Mexico. The impact created the Chicxulub crater and released energy far greater than any nuclear explosion humans have ever produced. Dust and debris filled the atmosphere. Sunlight was blocked, temperatures dropped, plants died, food chains collapsed. In a relatively short time, most dinosaurs disappeared. The mighty Tyrannosaurus rex, the armored Ankylosaurus, the horned Triceratops, and the long-necked giants all vanished. Only one group of dinosaurs survived, the small feathered ones that we now call birds. In a sense, dinosaurs never truly went extinct. They transformed. Looking back, it is clear why the Cretaceous stands out as the golden age of dinosaurs. It was a time when they reached their greatest sizes, evolved their most dramatic forms, and dominated the planet more completely than ever before. They filled every major land habitat. They adapted to rivers, forests, deserts, and polar regions. They developed horns, armor, sails, crests, feathers, and powerful jaws. They experimented with social behavior, nesting, and migration. They became masters of their world. The Cretaceous was not simply the end of the dinosaur story. It was the climax. It was the moment when millions of years of evolution reached their highest expression. The world was warmer, wilder, and more alive with reptilian giants than at any other time. It was an age of roaring predators, thundering herds, and endless green landscapes under a different sky. And although that age ended in fire and darkness, its legacy remains all around us. Every bird that takes flight is a reminder of that golden time. Every fossil discovered in rock layers tells a story of power, adaptation, and survival. The Cretaceous was the grand finale of the dinosaurs' long reign, the shining peak of their empire on Earth. More than 65 million years ago, the Earth was a very different place. The land was filled with enormous forests, wide rivers, and vast plains where life thrived in strange and wonderful forms. The air was thick with the calls of giant reptiles, the rustle of enormous ferns, and the low rumble of creatures far larger than anything we see today. Among these incredible beings, the most feared and fascinating were the great meat-eaters, the hunters that sat at the very top of the food chain. These creatures were the apex predators, the rulers of their domains, and among the most famous of all was the mighty Tyrannosaurus rex. Tyrannosaurus rex, often simply called T-Rex, was a dinosaur unlike any other. Standing over 12 meters long and more than 6 meters tall at the hips, this massive creature could weigh around 9 tons, which is about the weight of a small truck. Its skull alone could reach nearly 1.5 meters, and it was filled with enormous sharp teeth that could crush bone as easily as we bite into an apple. Every part of the T-Rex was designed for hunting and killing. Its legs were strong and muscular, built for speed despite its immense size, and its tail acted as a counterbalance, helping it turn quickly and maintain stability while chasing prey. Its tiny arms, though often the subject of jokes, were incredibly strong for their size, possibly used to hold struggling prey close while the jaws did the work. With a bite force stronger than any animal that has ever lived, Tyrannosaurus could snap through the bones of even the largest herbivores, leaving no doubt that it was at the top of the predator pyramid. T-Rex was not alone in being a terrifying predator. The world of the late Cretaceous period, which lasted from about 145 million to 66 million years ago, was full of fierce hunters. Other large carnivorous dinosaurs, such as the slightly earlier tyrannosaur relatives like Albertosaurus and Gorgosaurus, roamed what is now North America. In Asia, giant hunters like Tarbosaurus ruled their territories, showing that massive predators evolved in different parts of the world, each one adapted perfectly to its own environment. Some were built for speed, some for strength, and some combined both in terrifying ways. The diversity of these apex predators shows how nature, over millions of years, could shape life into terrifying forms of hunting perfection. These predators were not mindless killers. Many scientists now believe that creatures like T-Rex had sharp senses and possibly even complex behavior. Their large eyes suggest excellent vision, capable of spotting movement from long distances. Their brains, while not as large as ours, had regions that were highly developed for smelling, suggesting they could detect prey from miles away. Some researchers even propose that T-Rex might have been more than a lone hunter. There is evidence to suggest that, at times, they could have hunted in pairs or small family groups, coordinating attacks much like modern wolves. This would have made them even more formidable, able to take down enormous creatures like Triceratops, which could weigh over 10 tons, or Edmontosaurus, a massive duck-billed dinosaur. The prey of these giant hunters was just as fascinating. Large herbivorous dinosaurs filled the land, grazing in herds and constantly on the lookout for danger. Imagine a herd of Triceratops with their massive three-horned faces and armored frills, slowly moving across a forest clearing. Their size and horns were defensive, but nothing could guarantee safety from a hungry T-Rex. These herbivores had to rely on their senses, speed, and strength, as well as the safety of their herd to survive. The dance between predator and prey was eternal, a delicate balance that shaped the evolution of both groups. Just as T-Rex grew stronger and faster to catch its prey, herbivores developed larger horns, thicker armor, and keen senses to escape death. This evolutionary arms race was the driving force behind the incredible adaptations seen in both hunters and the hunted. The world these apex predators lived in was harsh and dynamic. The climate during the late Cretaceous was generally warmer than today, with no polar ice caps and higher sea levels. Vast inland seas split continents, creating islands and peninsulas that allowed dinosaurs to evolve in isolation, sometimes resulting in even stranger forms of life. Forests were dominated by towering conifers, ferns, and flowering plants, and rivers teemed with fish, turtles, and crocodile-like reptiles. In this rich and dangerous environment, survival was never guaranteed. For a T-Rex, each day required energy and skill. Finding food was a constant challenge, and even the largest predator had to compete with others. Injuries from fights, disease, and the unpredictability of nature could end a life suddenly, regardless of strength. Fossil evidence gives us a remarkable window into this world. Paleontologists have discovered bones of T-Rex with healed fractures, suggesting that even these massive creatures could survive injuries and continue hunting. Bite marks on other dinosaur bones indicate that they sometimes scavenged as well as hunted, taking advantage of opportunities whenever they arose. Tracks fossilized in mud show that T-Rex and other large predators could travel long distances, moving across floodplains, forests, and river valleys in search of prey. These fossils tell stories of struggle, power, and survival, painting a vivid picture of a world ruled by giants. Tyrannosaurs were not just predators, they were symbols of power and adaptation. Their rise illustrates one of the most fascinating chapters in the history of life. Over millions of years, small bird-like theropods evolved into enormous apex predators, perfecting hunting strategies, building powerful bodies, and developing incredible senses. They became the rulers of their ecosystems, shaping the lives of countless other creatures. Their dominance also influenced evolution itself. Prey species had to adapt, giving rise to armor, horns, and behavioral strategies, while other predators faced constant pressure to evolve, migrate, or risk extinction. The presence of these apex predators created a delicate and interdependent web of life, where every action had consequences across the ecosystem. While T-Rex captures our imagination today, it was part of a larger story of apex predators through time. Before the Age of Dinosaurs, giant carnivorous reptiles such as the Rauisuchians hunted in the Triassic period, and after the dinosaurs disappeared, mammals took over the role of top predators. Saber-toothed cats, giant bears, and enormous sharks all played similar roles in their own eras. By studying T-Rex and its contemporaries, scientists can understand not only the lives of these specific dinosaurs, but also the broader patterns of evolution, survival, and ecological balance that govern life on Earth. The fascination with Tyrannosaurus rex is not just scientific, it captures something deep in our imagination. When we imagine a T-Rex roaring across a misty floodplain, chasing a herd of hadrosaurs, or standing triumphantly over the remains of a massive Triceratops, we are witnessing a story that played out over millions of years. It is a story of power, survival, and the relentless march of life adapting to challenges. Movies, books, and museums bring these creatures to life, but the fossils themselves tell the most compelling story. Each bone, each footprint, and each tooth is a clue, a message from a time so long ago that it almost seems like another world. Even today, the shadow of Tyrannosaurus and other apex predators lingers in our culture and our minds. They represent the ultimate hunter, the pinnacle of evolutionary design, and the raw power of nature. Scientists continue to debate questions about their speed, intelligence, and behavior, uncovering new surprises with every fossil discovery. Feathered relatives of T-Rex have been found, suggesting that even these massive creatures were connected to the evolution of modern birds, bridging the gap between past and present in ways that challenge our understanding of life itself. In the end, the story of Tyrannosaurus rex and its fellow apex predators is one of awe and wonder. These creatures dominated their world, shaping ecosystems, driving evolution, and leaving behind a legacy that continues to captivate us millions of years later. They were not just hunters, they were engineers of the ecosystem, forces of nature that defined their age. Their power, adaptation, and mystery ensure that they will remain icons of the prehistoric world, inspiring curiosity, imagination, and respect for the incredible diversity and resilience of life on Earth. The rise of these predators reminds us of the delicate balance that exists in nature. Apex predators, whether in the age of dinosaurs or today, are essential to the health of ecosystems. They control populations, maintain diversity, and influence the behavior of other species. Without creatures like T-Rex, the ecosystems of the late Cretaceous would have been unrecognizable, lacking the dynamic tension between predator and prey that drives evolution forward. Their presence shaped the landscape, the forests, and the very life forms that shared the planet with them. Understanding them gives us insight into the deep past and into the forces that continue to shape life on Earth today. The fascination with apex predators extends beyond paleontology into philosophy and culture. They embody strength, skill, and survival, capturing human imagination and inspiring stories, myths, and legends. Tyrannosaurus rex, in particular, stands as a symbol of raw power, evolutionary brilliance, and the beauty of life adapted to its environment. From scientific research to popular media, the image of this towering hunter chasing its prey is one of the most enduring and compelling visions of prehistory. The Earth during the late Mesozoic era was a land of enormous creatures, vast forests, and endless plains where some of the most incredible animals to ever exist roamed freely. Among these giants, two groups of dinosaurs stand out as both awe-inspiring and practically engineered by evolution for survival. The horned dinosaurs, with Triceratops as their most famous representative, and the armored dinosaurs, with Ankylosaurus reigning supreme as a living fortress. Their development, their survival strategies, and their interactions with the world around them reveal a story of adaptation, resilience, and sometimes sheer ingenuity that spanned millions of years. The horned dinosaurs, or ceratopsians, were remarkable not only for their sheer size, but also for the extraordinary structures that adorned their heads. Triceratops, which translates as three-horned face, had a pair of long curved horns above its eyes and a smaller horn on its nose. Behind these striking features was a large, bony frill that extended from the back of the skull. Each of these adaptations had evolved for very practical purposes, shaped by countless generations of natural selection. Scientists studying the fossils have suggested that the horns and frill were used in defense against predators, as a visual display to assert dominance over rivals, and potentially to attract mates. Some paleontologists even argue that the frill may have had areas rich in blood vessels, allowing it to regulate body temperature or signal health and strength to others. The evolution of ceratopsians was gradual but fascinating. Early ancestors of Triceratops, appearing roughly 120 million years ago during the Cretaceous period, were smaller and less ornamented. They did not yet possess the enormous frills or the massive, intimidating horns. Over time, however, environmental pressures and the presence of predators encouraged these dinosaurs to develop ever more pronounced features. Fossil evidence shows a gradual enlargement of the skull, the development of robust horns, and the refinement of the frill's shape and size. By the late Cretaceous period, around 70 million to 66 million years ago, Triceratops had evolved into one of the largest ceratopsians, weighing between 6 and 12 tons and reaching lengths of up to 30 feet. Their bodies were built like living tanks, with strong, muscular limbs capable of supporting their enormous weight while allowing them to graze on tough vegetation, including cycads, ferns, and conifer needles. Triceratops lived in what is now North America, and fossil evidence suggests that they may have moved in herds or family groups. This social structure would have provided both protection and opportunities for complex behaviors. The horns could be used to fend off predators, such as Tyrannosaurus rex, which shared the same time and regions. These predators were massive, powerful, and terrifying hunters. But Triceratops had evolved to match these threats with a combination of size, strength, and weaponry. The frill at the back of their skull, in addition to serving as protection, may have allowed these animals to recognize one another or communicate visually across distances. Some researchers believe that young Triceratops could practice sparring with one another, gradually developing the skills they would need to survive into adulthood. While horned dinosaurs evolved defensive and social strategies that relied heavily on display and combat structures, another group of herbivores took a completely different evolutionary path. The ankylosaurs, armored dinosaurs designed almost like living fortresses. Among them, Ankylosaurus is the most famous, and for good reason. This dinosaur had a low, wide body covered in thick, bony plates embedded directly into its skin, forming nearly impenetrable armor. Its head, back, and sides were lined with these bony shields, and some species even had small spikes protruding from the armor. But what made Ankylosaurus especially unique was its tail. Ending in a massive club, it served as a powerful weapon capable of smashing the bones of any predator daring enough to attack. Ankylosaurus evolved during the very late Cretaceous period, around 66 million years ago, living in regions that today make up parts of North America. Measuring up to 30 feet in length and weighing between 6 and 8 tons, it was a formidable presence in its environment. Unlike Triceratops, Ankylosaurus relied less on social behavior and more on its physical defenses. Its armored body and tail club meant that even the most determined predators had to think twice before attacking. Fossilized remains suggest that its body was heavily muscled, particularly around the tail, allowing it to swing the club with extraordinary force. Paleontologists have calculated that a strike from an Ankylosaurus tail could easily break the leg bones of large predators or deliver a disabling blow to the skull of a smaller attacker. The evolutionary story of Ankylosaurus is a testament to the many paths nature can take to solve the problem of survival. While ceratopsians like Triceratops focused on horns, frills, and herd dynamics to evade predators and thrive, Ankylosaurs opted for a strategy based almost entirely on passive and active defense through armor and weaponry. These differences highlight the remarkable variety of adaptations that dinosaurs achieved over millions of years, shaped by environment, predation pressure, and available resources. The ecosystems in which Triceratops and Ankylosaurus lived were complex and dynamic. Forests of towering conifers, ferns, and cycads provided food and shelter for herbivores, while rivers and shallow seas dotted the landscape. Large predators, including Tyrannosaurus rex, roamed these regions, hunting anything that moved. The interplay between predator and prey drove the evolution of these herbivores, leading to the extraordinary features we associate with them today. For example, the heavy, bone-plated frill of Triceratops not only offered protection, but also acted as a shield during head-to-head confrontations with rivals or predators. Similarly, Ankylosaurus's tail club was not just a passive defense. Its very presence likely deterred attacks, shaping predator behavior over generations. The fossil record offers tantalizing glimpses into how these dinosaurs lived, interacted, and even grew. Triceratops fossils have been found in different stages of development, from hatchlings to fully grown adults, revealing how their horns and frills developed as they aged. Young Triceratops had small, undeveloped horns and frills, gradually growing more prominent with maturity. This development likely played a role in social hierarchies, allowing older, larger individuals to dominate younger ones. Ankylosaurus fossils, while rarer, show that their armor plates and tail clubs were present even in relatively young individuals, suggesting that protection was necessary from an early age. This may also indicate that young ankylosaurs were vulnerable to predation and needed immediate defense mechanisms to survive. Another fascinating aspect of these giants is how they coexisted with other herbivorous dinosaurs. During the late Cretaceous period, North America was home to a remarkable diversity of species. Horned dinosaurs included not only Triceratops but also other ceratopsians with different horn arrangements and frill shapes, each occupying slightly different ecological niches. Ankylosaurs, with their low-slung bodies and armored defenses, often browsed on low-lying vegetation, feeding on plants that taller ceratopsians might ignore. This ecological separation helped reduce direct competition for food and allowed multiple large herbivores to thrive in the same regions. The study of these dinosaurs has also revealed much about the broader patterns of evolution. Triceratops and Ankylosaurus illustrate how natural selection can take different forms to solve similar problems. Both had to survive in an environment dominated by formidable predators, yet their solutions were dramatically different. One developed elaborate cranial ornamentation and possibly complex social behaviors. The other developed a body armored like a tank with a built-in weapon. These differences underscore the creativity of evolution, demonstrating that there is rarely a single way to adapt to a challenging world. Scientists continue to learn new things about these dinosaurs through modern technologies such as CT scanning of skulls, biomechanical analysis of skeletons, and even the study of fossilized skin impressions. For Triceratops, CT scans of the skull have revealed intricate internal structures that may have supported strong jaw muscles, allowing it to chew tough, fibrous plants efficiently. Detailed studies of Ankylosaurus's tail and limbs have shown how muscle attachments and bone structure enabled precise and powerful tail swings, turning the dinosaur's natural defenses into a dynamic weapon. Even traces of fossilized skin provide clues about how these animals looked in life, suggesting that ankylosaurs had a mosaic of bony plates and possibly keratinous coverings that added both protection and a degree of camouflage. The end of the Cretaceous period, around 66 million years ago, brought dramatic changes to the Earth, culminating in one of the most famous extinction events in history. A massive asteroid impact in what is now the Yucatan Peninsula in Mexico triggered widespread fires, tsunamis, and a nuclear winter effect that disrupted global climates. These sudden changes proved catastrophic for many species, including the horned and armored dinosaurs. Despite millions of years of evolutionary success, both Triceratops and Ankylosaurus, along with countless other species, vanished from the fossil record, leaving behind only bones, armor plates, and the imagination of scientists and enthusiasts to reconstruct their incredible lives. Yet even in extinction, these dinosaurs left a profound legacy. Their unique adaptations, their sheer scale, and the sophistication of their defense mechanisms continue to inspire paleontologists and the public alike. Exhibitions in museums, detailed illustrations, and even films and documentaries have brought Triceratops and Ankylosaurus to life, allowing people to imagine the thunderous sound of 30-foot-long creatures moving through prehistoric forests, or the swing of a tail club that could smash a predator's leg. Through these representations, the story of evolution and survival that played out over tens of millions of years remains vivid and compelling. the study of horned and armored dinosaurs also provides a window into the broader principles of biology and adaptation. For instance, Triceratops shows how physical structures can serve multiple roles, from defense to social signaling, while Ankylosaurus demonstrates the power of passive and active defenses in ensuring survival. Both cases illustrate the dynamic interplay between environment, behavior, and physiology, teaching lessons that extend far beyond paleontology. By understanding how these giants thrived, scientists gain insight into the mechanisms that drive evolution, the pressures that shape ecosystems, and the astonishing diversity of life that Earth has supported over time. Triceratops and Ankylosaurus, in particular, represent the pinnacle of two evolutionary strategies that coexisted during the late Cretaceous period. One relied on horns and frills, combining intimidation with social complexity, while the other relied on armor and brute strength, creating a mobile fortress. Their success was not merely a matter of size, it was the result of millions of years of trial, error, and refinement. Every curve of a horn, every plate of armor, and every swing of a tail club tells a story of adaptation in a world filled with danger and opportunity. Even today, the fascination with these dinosaurs continues to grow. Fossils continue to be discovered in North America, and each new find adds another piece to the puzzle, revealing subtle variations in anatomy, growth patterns, and even potential behaviors. Triceratops specimens show that individual variation was significant, with differences in horn length, frill shape, and skull robustness, hinting at the complexity of their social interactions. Ankylosaurus fossils suggest that these armored giants may have evolved slightly different armor patterns depending on their habitat or the presence of specific predators, demonstrating that even within a single genus, adaptation could be remarkably fine-tuned. The story of life on Earth is filled with extraordinary creatures, but few have captured the imagination of humans quite like the sauropods. These are the enormous, long-necked dinosaurs that seem to belong not just to the land, but to another, almost mythical world. Among them, one name stands out as a symbol of size, power, and survival: Argentinosaurus. To truly understand how these giants, the long-necked survivors, managed to thrive for millions of years, we must journey back to a time when the Earth was a very different place, a world ruled by giants, where forests stretched endlessly, rivers carved deep paths through the land, and the sky was filled with the cries of creatures both massive and strange. Imagine the Earth around 100 million years ago, during the late Cretaceous period. The continents were slowly drifting towards the positions we know today, but the world was warmer, and there were no polar ice caps. Vast forests covered much of the land, with trees towering like skyscrapers in modern cities. Ferns, cycads, and conifers grew in abundance, providing an endless buffet for the enormous herbivores that roamed the Earth. It was in this lush, vibrant world that sauropods like Argentinosaurus lived, thrived, and evolved. These creatures were not just large, they were massive, their bodies stretching over 100 feet from head to tail, their necks like long, flexible bridges reaching high into the treetops to pluck leaves that other animals could not reach. Argentinosaurus, in particular, is believed to have been one of the largest animals to ever walk the Earth, tipping the scales at perhaps 100 tons, or roughly the weight of 20 modern African elephants combined. But size alone did not guarantee survival. To remain the dominant herbivores of their time, sauropods had to overcome many challenges, from finding enough food to defending themselves against predators, from reproducing successfully to adapting to changing climates. One of the most fascinating aspects of these long-necked giants is how perfectly their bodies were designed for the life they led. Their long necks were not just impressive, they were tools of survival. By evolving necks that could stretch high into the trees, sauropods could access food that was out of reach for most other creatures. This gave them a tremendous advantage, especially in times when food was scarce on the forest floor. They could browse from treetops, moving gracefully, or sometimes not so gracefully, through the forest, selecting the most nutritious leaves, shoots, and branches, while smaller herbivores competed over the vegetation below. The structure of a sauropod's body was a marvel of natural engineering. Despite their enormous size, their skeletons were surprisingly lightweight, thanks to bones that were hollow, much like the structure of modern bird bones. This made it possible for them to carry long necks and massive tails without collapsing under their own weight. Their legs were like columns, thick and sturdy, built to support the immense weight of their bodies as they walked for miles in search of food and water. Some scientists believe that Argentinosaurus could have eaten for up to 16 hours a day just to sustain its enormous body, consuming hundreds of pounds of vegetation each day. Their digestive systems were equally remarkable, likely allowing them to extract as many nutrients as possible from tough, fibrous plants that would have been difficult for other animals to digest. Reproduction, too, played a crucial role in their survival. Sauropods laid eggs, often in large nests, and some species may have laid dozens at a time. While hatchlings were small compared to their parents, they were born ready to survive. Even though young sauropods were vulnerable to predators, they grew at astonishing rates, sometimes reaching the size of a small car within a few years. This rapid growth rate not only protected them from most predators, but also allowed populations to recover quickly, even if some individuals were lost to natural dangers or predation. Speaking of predators, life for a giant like Argentinosaurus was not without danger. Carnivorous dinosaurs prowled the forests, some of them almost as enormous as the herbivores they hunted. Yet the sheer size of Argentinosaurus and other adult sauropods made them formidable. Few predators could tackle a fully grown adult, and their long tails could serve as powerful whips, capable of fending off attackers. Herd behavior may have also been a survival strategy. By traveling in groups, sauropods could protect the young and vulnerable, and the sight of a herd of these colossal creatures moving together would have been an intimidating display to any predator brave enough to approach. The survival of sauropods like Argentinosaurus was not just a story of physical adaptation, it was also a story of environmental opportunity. The late Cretaceous was a time of abundance in many regions, with warm temperatures and flourishing plant life providing ample resources for the giants. Yet, these environments were not static. Climate shifts, volcanic activity, and changing sea levels meant that sauropods had to be resilient and adaptable. Fossil evidence shows that these dinosaurs were capable of migrating over long distances, moving to areas where food was plentiful and avoiding regions where conditions had become harsh. Their ability to travel long distances and exploit diverse habitats was a key factor in their long-term success. Another aspect of their survival lies in evolution itself. Sauropods existed for over 100 million years, a testament to their evolutionary success. During this time, they developed countless variations in size, shape, and behavior, allowing them to exploit different ecological niches. Some evolved extremely long necks, while others developed specialized teeth for particular types of plants. Some species adapted to life in open plains, while others preferred forested areas. This diversity meant that even if one species faced challenges or local extinction, others could continue to thrive, ensuring the persistence of the sauropod lineage. Fossil discoveries have been crucial in revealing the secrets of these magnificent creatures. Argentinosaurus, for instance, was first discovered in Argentina in the 1980s. Paleontologists uncovered partial skeletons, including massive vertebrae and limb bones, which hinted at the incredible size of this dinosaur. By studying these fossils, scientists have been able to reconstruct not only the appearance of Argentinosaurus, but also aspects of its behavior, growth, and lifestyle. Modern technology, such as computer modeling and biomechanical analysis, allows researchers to simulate how these dinosaurs moved, how their hearts and lungs may have worked, and how they could have survived in their ancient environments. Each discovery adds another piece to the puzzle, bringing the long-necked giants closer to life in our imagination. Despite their size and dominance, the story of sauropods is also a story of vulnerability. The end of the Cretaceous period, around 66 million years ago, brought massive changes to the Earth. A catastrophic event, most likely an asteroid impact combined with volcanic activity and climate shifts, caused widespread extinction. Many of the largest species, including Argentinosaurus and other titanic sauropods, vanished forever. Yet, their legacy lives on, not just in the fossils preserved in rock, but in the birds that soar above us today, the distant descendants of their dinosaur ancestors. In a sense, the long-necked survivors continue to exist, transformed into creatures of flight, reminding us of the incredible resilience and adaptability of life on Earth. The fascination with sauropods also lies in what they teach us about life and survival. They demonstrate how size can be both an advantage and a challenge. They show how evolution can shape creatures in extraordinary ways to fit their environments perfectly. They remind us of the importance of adaptation, resilience, and the delicate balance between an organism and its world. The story of Argentinosaurus, in particular, is a story of extremity, of living at the edge of physical possibility, of thriving against odds, and of leaving a mark on the planet that continues to inspire wonder millions of years later. To truly appreciate the world of Argentinosaurus, we must try to imagine it not just as a series of bones in a museum, but as a living, breathing ecosystem. Picture a warm, sunlit forest with ferns carpeting the ground and massive conifers stretching toward the sky. In the distance, a herd of Argentinosaurus moves slowly but deliberately, their long necks reaching high into the trees, plucking leaves with precise, almost gentle movements. Their tails sway behind them like massive pendulums, brushing aside smaller vegetation as they move. The sound of their footsteps is like distant thunder, felt more than heard, shaking the earth beneath them. Nearby, smaller herbivores scatter at their approach, while carnivorous predators watch from the shadows, calculating but wary. This is a world where size, strategy, and adaptation converge, where survival is both a challenge and an art. Furthermore, the lives of these dinosaurs were likely filled with social interaction and complex behavior. Herds provided protection, and there may have been communication between individuals through vocalizations or visual signals. Some scientists speculate that long necks were not only for feeding, but also for display, allowing individuals to assert dominance or attract mates. The sheer scale of these animals meant that they experienced the world in ways completely different from humans, perceiving threats and opportunities across vast distances, interacting with an environment that was as immense as they were. Modern paleontology continues to reveal surprising facts about sauropods. For example, the study of bone microstructure shows that these animals could grow astonishingly quickly, with young sauropods gaining several feet in height each year. This rapid growth required a highly efficient metabolism and a diet that could support such energy demands. Fossilized trackways provide insight into their movement and behavior, showing evidence of herd migration, social grouping, and even the possibility of protective formations around the young. Each fossil, each discovery, paints a picture of resilience, adaptation, and survival in a world both beautiful and perilous. Argentinosaurus, as one of the largest sauropods, represents the pinnacle of these long-necked survivors. Its enormous size made it nearly impervious to most predators and allowed it to reach resources inaccessible to other creatures. Its evolution reflects the ingenuity of nature, finding solutions to the challenges of feeding, growth, and reproduction on a scale almost unimaginable. It also reminds us of the fragility of life, as even the most successful species are ultimately subject to the whims of catastrophic events and environmental change. Long ago, the earth was dominated by plants that did not flower. Ferns with delicate, feathery leaves waved in the wind, Mosses formed thick green carpets over rocks and soil, and towering conifers, the ancestors of modern pine trees, stood like silent guardians of forests. These plants, though beautiful and vital in their own way, had a certain limitation. They did not produce flowers. They reproduced through spores or cones, relying heavily on the wind to carry their pollen and seeds from one place to another. Life on Earth at that time was robust and full, yet the world seemed to be waiting for something more, something that would dramatically alter the face of the land, the air, and even the life of creatures that roamed it. That something, as it turned out, was the sudden rise of flowering plants, known to scientists as angiosperms. Angiosperms, or flowering plants, appeared relatively suddenly in the fossil record, around 140 million years ago, during the early part of the Cretaceous period. The first flowers were not the elaborate roses, orchids, or lilies we know today. Instead, they were small, simple, and unassuming, tiny blossoms that might have gone unnoticed by anything larger than a passing insect. Yet, even in their modest beginnings, these early flowering plants had something revolutionary, a new way to reproduce. Unlike conifers, which released clouds of pollen into the air and relied on chance for fertilization, flowering plants developed intricate flowers that attracted animals, particularly insects, to help them spread their pollen. This partnership between plants and animals, known as pollination, changed everything. Imagine a world where a small, inconspicuous plant produces a bloom that is perfectly shaped to entice a certain type of insect. The insect, drawn to the flower's color, scent, or nectar, lands delicately upon it. As it searches for food, pollen sticks to its body, and when the insect flies to another flower of the same species, it unintentionally transfers the pollen, fertilizing the plant. This system, which may seem ordinary today, was extraordinary in its time. It allowed flowering plants to reproduce more efficiently and to colonize areas where wind-pollinated plants could not thrive. Suddenly, there was a new force in the plant world, quietly but rapidly expanding its territory. The spread of flowering plants did not happen in isolation. It coincided with a period of great change on Earth. The Cretaceous period was marked by warmer global temperatures, higher levels of carbon dioxide in the atmosphere, and rising sea levels that created shallow inland seas. Forests of conifers and ferns still dominated much of the land, but flowering plants began to weave themselves into these ecosystems, filling gaps in sunlight and soil that other plants could not exploit as effectively. Their ability to attract pollinators gave them a significant advantage, and their seeds, often encased in fleshy fruit, encouraged animals to eat and disperse them. Birds, early mammals, and insects all played a part in helping these plants spread across continents. In a surprisingly short span of geological time, flowering plants began to replace many older plant forms and reshape the structure of forests, plains, and wetlands. One of the remarkable aspects of flowering plants is the extraordinary diversity they brought to the earth. While ferns, mosses, and conifers were limited in form and function, angiosperms diversified into countless shapes, sizes, and ecological roles. Some, like the giant magnolias of the Cretaceous, grew into towering trees, while others remained small and ground-hugging, covering the forest floor with dense mats. Some developed thick, waxy leaves to survive in arid climates, while others evolved delicate, feathery foliage suited to wet, tropical environments. Flowering plants did not just occupy existing ecological niches, they created new ones, offering habitats, food, and shelter for countless other organisms. The rise of flowering plants was not merely a botanical event, it was a catalyst for ecological revolution. Consider the insects, which were among the first to notice the new flowers. The relationship between flowering plants and insects is one of the most remarkable partnerships in the history of life. Many insects, such as bees, beetles, and butterflies, evolved alongside flowering plants, adapting to the shapes, colors, and scents of specific flowers. In turn, flowers evolved to better accommodate their insect visitors, leading to an intricate dance of co-evolution. Some flowers developed long, narrow tubes that only insects with matching mouthparts could reach, ensuring that only certain species could pollinate them. Others produced bright colors or alluring scents to attract a wider range of pollinators. The consequences of these relationships were profound. They fueled the diversification of both plants and insects, setting the stage for the ecosystems we recognize today. The spread of flowering plants also had a dramatic impact on the diets and evolution of animals. Herbivorous dinosaurs, which had once grazed primarily on conifers and ferns, began encountering new sources of food. Seeds and fruits offered higher nutritional value, and animals that could exploit these resources gained an advantage. When the massive extinction event struck at the end of the Cretaceous, wiping out most dinosaurs, it was the smaller mammals, birds, and insects that thrived, many of whom had already developed close relationships with flowering plants. After the extinction, flowering plants continued to spread, dominating landscapes that were no longer home to giant herbivores. Their rise created opportunities for new species to evolve and for ecosystems to become more complex and interconnected than ever before. Another remarkable feature of flowering plants is their reproductive versatility. Unlike gymnosperms, whose seeds are often exposed and rely on wind or gravity, flowering plants can package seeds within fruit, offering protection and aiding in dispersal. Fruits can be eaten by animals, carried away and excreted in new locations, sometimes far from the parent plant. Some seeds are designed to float on water, enabling colonization of distant shores. Others can lie dormant for years, waiting for the right conditions to germinate. This versatility allows flowering plants to adapt to a vast array of environments, from tropical rainforests to arid deserts to temperate woodlands, outcompeting many older plant groups and solidifying their dominance across the globe. By the time the Paleogene period arrived around 66 million years ago, flowering plants had established themselves as the dominant plant group on Earth. Forests were now rich with flowering trees, shrubs, and herbs. Grasses began to appear, slowly transforming open plains and savannas. Flowers covered the land in colors and scents that had never existed before, providing food and shelter to a growing diversity of animals. Birds, insects, and mammals all benefited from this explosion of life, and their own evolution was shaped by the new abundance of resources. The rise of flowering plants was not simply a botanical phenomenon, it was a turning point in the history of life itself. The impact of flowering plants continues to this day. Nearly 90% of modern plant species are angiosperms, and they provide the foundation for most terrestrial ecosystems. Our diets, economies, and cultures are intertwined with flowering plants. They provide food, medicine, timber, and raw materials, and they shape the landscapes we live in. From the apple orchards of Europe to the rice paddies of Asia, from the savannas of Africa to the tropical rainforests of South America, flowering plants dominate. They are, in many ways, the architects of the modern world, having transformed the Earth in ways that no other group of organisms has. Yet, despite their current dominance, the story of flowering plants began humbly. Tiny, simple flowers, evolving in obscurity, created partnerships with insects and animals that allowed them to flourish. Through co-evolution, natural selection, and sheer adaptability, they rose to dominate continents and oceans alike. Their success reshaped landscapes, climates, and the lives of creatures that depended on them, leaving a lasting legacy that continues to this day. In reflecting upon the rise of flowering plants, one realizes the profound nature of innovation in the natural world. A small change, a flower, an enticing scent, a sweet nectar, can ripple across millions of years and reshape entire ecosystems. Flowering plants exemplify how life is not static but dynamic, constantly adapting, evolving, and creating opportunities for new forms of life to emerge. They remind us that evolution is not just a story of survival but of transformation, collaboration, and the beauty of complexity arising from simplicity. The legacy of angiosperms also demonstrates the interconnectedness of life. Flowers would not thrive without pollinators. Pollinators would not flourish without flowers. Fruits and seeds nourish herbivores, who, in turn, disperse seeds and fertilize soils. Forests shaped by flowering plants influence rainfall, temperature, and even the chemistry of the atmosphere. Every leaf, blossom, and seed contributes to a vast, intricate web of life that continues to support the diversity and resilience of our planet. It is remarkable to think that all of this began with plants that may have seemed insignificant in their early days. Small flowers that hid in the shade of towering ferns or clung to the edges of streams. From these humble beginnings, flowering plants achieved something extraordinary. They transformed the face of the earth. They created new ecosystems, reshaped food chains, and fostered the evolution of countless species, including our own. Today, when we admire a meadow in full bloom, wander through a forest of flowering trees, or enjoy a fruit from a distant orchard, we are witnessing the living legacy of that ancient transformative rise. The flowering plants are more than just plants. They are storytellers of evolution, bearers of beauty, and architects of life on Earth. Their rise reminds us of the power of adaptation, the importance of collaboration, and the endless possibilities that emerge when life finds new ways to flourish. The partnership between insects and flowering plants is one of the most important relationships in the natural world. It changed the shape of forests, the look of meadows, and even the food that humans eat today. This connection did not form quickly. It developed slowly over a very long time, as both insects and plants changed step by step, each influencing the other in a powerful process known as coevolution. Coevolution means that two different groups of living things affect each other's development. As one changes, the other changes too. In the case of insects and flowering plants, this back-and-forth relationship reshaped life on land. Before flowering plants became common, the world was dominated by other kinds of plants. During the time known as the Jurassic period and even earlier in the Triassic period, many landscapes were filled with ferns, cycads, conifers, and other plants that did not produce flowers. These plants reproduced mostly by using the wind to carry pollen. Wind pollination works, but it is not very precise. Plants must produce huge amounts of pollen because much of it is wasted. Only a small portion lands on the correct plant. Then, during the period known as the Cretaceous period, which began about 145 million years ago, flowering plants, also called angiosperms, began to appear and spread. At first, they were not very common, but over time they expanded into many environments. They developed new shapes, colors, and scents. They also formed a close relationship with insects, which helped them reproduce more effectively than wind-pollinated plants. Insects had already been living on land for hundreds of millions of years before flowering plants appeared. The earliest insects evolved during the Devonian period, and they became more diverse during the Carboniferous period. At that time, there were giant dragonflies and many other early insect groups. These insects fed on plant material, spores, or other insects. Some of them likely visited early seed plants to feed on pollen or plant fluids. Even before true flowers existed, certain insects were already interacting with plants in ways that prepared the ground for a deeper partnership. When flowering plants began to spread during the early part of the Cretaceous period, they brought something new to the natural world: flowers. A flower is not just a pretty structure, it is a complex reproductive organ. Inside a flower are parts that produce pollen and parts that receive pollen. For fertilization to happen, pollen must move from one flower to another of the same species. Wind can do this, but insects can do it more directly and more efficiently. At first, some insects probably visited flowers simply to feed. Flowers produce nectar, a sweet liquid rich in sugars. Nectar is a powerful reward. It provides quick energy, which insects need for flying. flowers also produce pollen, which contains proteins and other nutrients. Insects that fed on pollen and nectar would accidentally brush against the flower's reproductive parts. Pollen grains would stick to their bodies. When these insects flew to another flower, some of that pollen would rub off, completing the process of pollination. Over time, natural selection strengthened this relationship. Plants that were better at attracting insects reproduced more successfully. Insects that were better at finding and using flowers gained more food and survived in greater numbers. This back-and-forth process led to the development of amazing adaptations on both sides. Bees are among the most famous pollinators. They belong to a group of insects known as Hymenoptera, which also includes ants and wasps. Bees likely evolved from wasp-like ancestors that originally hunted other insects. At some point, certain wasps began feeding on pollen and nectar instead of prey. This shift in diet was a major turning point. It led to the evolution of bees as specialized pollinators. One of the key features that helped bees become effective pollinators is their hairy bodies. The tiny hairs on a bee's body are branched, which helps pollen grains stick more easily. Bees also developed special structures for carrying pollen, such as pollen baskets on their hind legs. These baskets allow them to gather large amounts of pollen and transport it back to their nests. While collecting pollen for food, bees also move pollen from flower to flower, helping plants reproduce. Different types of bees evolved in different ways. Some bees are solitary, meaning each female builds her own nest and gathers food for her own young. Others, like honeybees, live in large colonies with thousands of individuals. Social living allowed honeybees to share information about food sources. For example, the species known as Apis mellifera performs a special movement called the waggle dance. This dance tells other bees the direction and distance of a rich flower patch. Such complex behavior shows how deeply connected bees are to flowering plants. Butterflies and moths are also important pollinators. They belong to the order Lepidoptera. Their long tube-like mouthparts, called proboscises, allow them to drink nectar from deep inside flowers. Some flowers evolved long tubular shapes that match the length of a butterfly's or moth's proboscis. This matching of shapes is a clear example of coevolution. A famous example involves the orchid Angraecum sesquipedale. This orchid has an extremely long nectar spur. The naturalist Charles Darwin predicted that there must be a moth with a tongue long enough to reach the nectar at the bottom. Years later, scientists discovered such a moth, confirming his idea. Beetles are among the oldest pollinators. In fact, some scientists believe that beetles were visiting plants even before true flowers evolved. Beetle-pollinated flowers often have strong scents and sturdy structures. Beetles sometimes chew on flower parts, so these flowers tend to be tough. This type of pollination is sometimes called mess and soil pollination because beetles can be clumsy visitors. Flies also play a role in pollination. Some flies are attracted to flowers that smell like rotting meat. These flowers use scent to trick flies into visiting them. The flies think they have found a place to lay eggs, but instead they help the plant transfer pollen. This shows that pollination does not always depend on sweet smells and bright colors. Sometimes it involves clever deception. As flowering plants spread during the Cretaceous period, they began to transform ecosystems. They created new habitats and new food sources. Insects diversified rapidly during this time. The fossil record shows a sharp increase in the variety of insect species during the same period when flowering plants became dominant. This suggests that the rise of flowers helped drive the evolution of many insect groups. Colors played an important role in this partnership. Many flowers developed bright petals to attract insects. Bees, for example, can see ultraviolet light, which humans cannot see. Some flowers have ultraviolet patterns that guide bees toward their nectar. These patterns are like landing strips, pointing directly to the center of the flower. This visual communication between plant and insect is highly refined. Scent also became important. Flowers produce complex mixtures of chemicals that create distinct smells. Different insects are attracted to different scents. By adjusting their scent, flowers can target specific pollinators. In turn, insects developed sensitive antennae that allow them to detect these smells from a distance. Timing became another factor in coevolution. Some flowers open during the day, attracting bees and butterflies. Others open at night, attracting moths or bats. Night-blooming flowers are often pale or white, making them easier to see in low light. They may produce stronger scents to guide nocturnal pollinators. The relationship between insects and flowering plants is not always perfectly balanced. Sometimes insects take nectar without transferring pollen. Sometimes plants evolve defenses to control which visitors they allow. Some flowers have structures that ensure only certain insects can reach the nectar. This limits waste and increases successful pollination. Over tens of millions of years, this partnership shaped entire landscapes. Meadows filled with wildflowers supported countless bees, butterflies, and other insects. Forests developed complex layers of flowering shrubs and trees. Fruit-bearing plants spread widely, providing food for animals. Many animals that eat fruits help disperse seeds, adding another layer to the network of life. The impact of insect pollination reaches all the way to human society. Many crops depend on insect pollinators. Apples, almonds, berries, and many vegetables rely on bees and other insects to produce fruit. Without pollinators, harvests would shrink, and food would become more expensive and less varied. This shows that the ancient partnership between insects and flowers continues to support life today. However, this relationship is under threat in modern times. Habitat loss, pesticide use, climate change, and disease have reduced insect populations in many parts of the world. When pollinators decline, plants suffer as well. The balance that developed over millions of years can be disrupted in a short time. Understanding how insects and flowering plants evolved together helps us see how connected life truly is. What began as simple feeding visits grew into a deep and complex partnership. Flowers shaped insects. Insects shaped flowers. Together they painted the land with color, filled the air with movement, and built ecosystems rich with life. This partnership is not just a detail of natural history. It is one of the great engines of biodiversity. It shows how cooperation, guided by natural selection, can create beauty, complexity, and abundance. From the smallest wildflower in a field to the buzzing of a bee in a garden, the legacy of this ancient alliance continues, reminding us that life on Earth is woven together in delicate and powerful ways. The sky over the ancient world was once filled with living wings that cast enormous shadows across forests, rivers, deserts, and shallow seas. These wings did not belong to birds, and they were not supported by feathers. They belonged to pterosaurs, the first vertebrates in Earth's history to achieve true powered flight. These extraordinary flying reptiles dominated the air for well over 150 million years, shaping entire ecosystems from above. They soared over coastlines, glided across inland seas, circled above herds of dinosaurs, and nested on cliffs that overlooked warm tropical waters. Among them were giants so large that their wings stretched as wide as a small airplane. One of the most astonishing of all was Quetzalcoatlus, a creature whose very size challenges the limits of imagination. Pterosaurs first appeared during the late part of the Triassic period, more than 200 million years ago. At that time, the world's continents were joined together in a vast supercontinent known as Pangaea. The climate was often hot and dry, with broad deserts and seasonal rains. Dinosaurs were just beginning to rise in importance, small and lightly built compared to the giants that would come later. In this world of change and competition, one group of reptiles developed a remarkable solution to survival. They took to the air. Their bodies were built in a way that was both delicate and powerful. The most important feature of a pterosaur was its wing. Unlike birds, whose wings are made of feathers attached to arms with many short fingers, pterosaurs had a single finger that grew incredibly long. This fourth finger stretched outward and supported a thin membrane of skin called the patagium. This membrane ran from the tip of that long finger down to the body and even to the hind legs. Some species also had an additional membrane between their legs that may have helped with steering. The wing was not just loose skin. It was strengthened by fibers and muscles that allowed fine control in the air. It was flexible, able to change shape depending on whether the animal was flapping, gliding, or landing. The bones of pterosaurs were light and hollow, much like the bones of birds. This made their bodies lighter without sacrificing strength. Inside the bones were air spaces connected to the lungs, which helped reduce weight and improve breathing efficiency. Their chests were deep, providing room for strong flight muscles. Their shoulders were arranged in a way that allowed a wide range of wing motion. Every part of their skeleton showed signs of adaptation for life in the air. Their heads were often long and narrow, sometimes ending in sharp beaks filled with teeth. Some had no teeth at all. Many had elaborate crests made of bone or soft tissue that rose from their skulls like sails or blades. These crests varied widely in size and shape. In some species they were small ridges, in others they were enormous, towering above the head and possibly used for display, species recognition, or attracting mates. The exact purpose of many of these crests is still debated, but they clearly played an important role in pterosaur life. Over time, pterosaurs evolved into a wide variety of forms. Early species were often small, with wingspans of only a few feet. They may have fed on insects, catching them in flight or picking them from leaves. As millions of years passed, new groups appeared. Some became fish hunters, flying low over the water and dipping their beaks into the surface to snatch prey. Others may have scavenged, walking along shorelines and feeding on carcasses. Some developed long jaws filled with needle-like teeth, perfect for gripping slippery fish. Others evolved broad, toothless beaks that may have been suited for crushing shellfish or probing into mud. One well-known fish-eating pterosaur was Pteranodon. This creature lived during the late Cretaceous period and had a long, pointed beak with no teeth. It also had a backward-pointing crest on its head, which may have helped with balance in flight. Its wingspan could reach more than 20 feet, making it one of the larger flying animals of its time. Fossils of this species have been found in what was once a vast inland sea that divided North America. These fossils suggest that Pteranodon spent much of its life over open water, soaring like a modern seabird. Yet even Pteranodon was not the largest. That title belongs to the Ajdarchids, a group of pterosaurs that included some of the most enormous flying animals ever known. Among them was Quetzalcoatlus. Named after an ancient feathered serpent god of Mesoamerican mythology, this pterosaur lived during the very end of the Cretaceous period. Its wingspan may have reached close to 40 feet, roughly the size of a small aircraft. When standing on the ground, it may have been as tall as a giraffe. Its neck was long and stiff, and its head was enormous, with a long pointed beak. The size of Quetzalcoatlus raises fascinating questions. How could such a giant creature fly? The answer lies in the unique structure of its body. Despite its size, it was built lightly. Its bones were thin-walled and hollow. Its wing membrane was supported by strong fibers. Its muscles were likely powerful enough to launch it into the air. Some scientists believe it used all 4 limbs to push off the ground in a powerful leap, unfolding its wings as it rose. This method, called quadrupedal launch, may have allowed even the largest pterosaurs to become airborne. Once in the air, giants like Quetzalcoatlus probably relied heavily on soaring. By riding rising columns of warm air known as thermals, they could gain height without constant flapping. From high above, they could glide for long distances, scanning the land below. Their long necks and sharp beaks may have allowed them to pick up small animals from the ground. Some researchers think that Quetzalcoatlus may have walked on land like a stork, hunting small dinosaurs, mammals, or other prey in open environments. The world in which these giants lived was dramatically different from today. During much of the Cretaceous period, global temperatures were warmer. There were no large ice caps at the poles, sea levels were higher, and shallow seas covered large parts of continents. Lush forests and broad coastal plains offered rich feeding grounds. In such conditions, flying reptiles found many opportunities. Pterosaurs were not only creatures of size and power, they were also animals of subtle beauty and diversity. Fossil evidence suggests that many species were covered in a coat of fine hair-like filaments called pycnofibers. These structures were not feathers like those of birds, but they likely provided insulation. This suggests that pterosaurs may have been warm-blooded, able to control their body temperature and remain active in a range of conditions. A warm-blooded metabolism would have been helpful for flight, which requires a great deal of energy. Their eyes were often large, suggesting keen vision. In the air, sharp eyesight would have been essential for spotting prey or avoiding danger. Their brains show signs of well-developed regions related to balance and coordination. Flying requires constant adjustments, and pterosaurs were clearly well equipped for this challenge. Life for a pterosaur began in an egg. Fossilized eggs have been discovered in several parts of the world. These eggs had soft shells, more like those of some modern reptiles than the hard shells of birds. The young that hatched from them appear to have been well developed, possibly able to fly not long after birth. If this is true, pterosaur parents may not have needed to provide long-term care in the way many birds do today. As time passed, pterosaurs shared the skies with early birds. The first true birds appeared during the Jurassic period. One famous early bird is Archaeopteryx. Although birds and pterosaurs both flew, they were not closely related. Birds evolved from small feathered dinosaurs, while pterosaurs belonged to a separate branch of reptiles. For millions of years, these two groups coexisted. In some environments, they may have competed for food. In others, they may have occupied different ecological roles. By the end of the Cretaceous period, pterosaurs had become highly specialized. Many of the smaller forms had disappeared, leaving mostly large species. Then came one of the most dramatic events in Earth's history. Around 66 million years ago, a massive asteroid struck the planet, causing fires, darkness, and rapid climate change. This event marked the end of the non-avian dinosaurs and many other forms of life. Pterosaurs also vanished during this catastrophe. Unlike birds, which survived and later flourished, the flying reptiles did not recover. The extinction of pterosaurs marked the end of a long and remarkable chapter in the story of life. For more than 150 million years, they had ruled the skies. They had evolved from small, lightly built gliders into some of the largest flying animals ever known. They had adapted to coastlines, forests, deserts, and inland seas. They had grown crests, lost teeth, gained size, and developed extraordinary flight abilities. Today, we know them only from fossils. These fossils are often fragile, for their bones were thin and easily broken. Many specimens are flattened, pressed into rock like delicate shadows. Yet from these remains, scientists have reconstructed their bodies and imagined their movements. Museums display their skeletons suspended from ceilings, wings outstretched, giving visitors a sense of their grandeur. The study of pterosaurs continues to reveal new discoveries. Each new fossil can change our understanding. Some recent finds have shown that certain species had more complex wing structures than once believed. Others have provided clues about color patterns or growth stages. As technology improves, scientists can scan fossils in detail, building digital models that help test ideas about flight and behavior. The story of pterosaurs is a story of innovation. They were pioneers of the air, opening a world that no vertebrate had conquered before them. Their success shows how evolution can produce solutions that seem almost impossible. From a reptile ancestor walking on the ground, nature crafted a creature capable of soaring across continents. Imagining the sky filled with these reptiles is both thrilling and humbling. enormous forms like Quetzalcoatlus drifting high above a Cretaceous plain, smaller species darting between trees, fish hunters skimming the surface of warm seas. Together they formed a living tapestry overhead. Their shadows would have swept over herds of horned dinosaurs and armored giants. Their calls may have echoed along cliffs and beaches. Though they are gone, their legacy remains in the rocks beneath our feet and in the curiosity they inspire. Every fossil wing bone tells a story of lift and motion. Every skull crest hints at color and display. Every discovery reminds us that the history of life is richer and stranger than we often imagine. The pterosaurs were true rulers of the air, masters of a realm that demands precision, strength, and grace. In their long reign, they proved that even reptiles could take to the sky and transform it into their domain. The oceans of the Cretaceous were not empty blue deserts the way they may seem from the surface today. They were alive with motion, color, sound, and danger. Beneath the waves swam some of the most extraordinary and terrifying creatures that have ever existed. These were not fish, and they were not dinosaurs. They were marine reptiles, air-breathing hunters that had returned to the sea long before the Cretaceous began. Among the most famous of these ocean rulers were creatures like Mosasaurus and the long-necked plesiosaurs, animals so strange and powerful that they still capture the imagination today. To understand these monsters, we must first imagine what the world looked like during the Cretaceous. The continents were not arranged as they are now. The supercontinent Pangaea had already begun to split apart in earlier ages, and during the Cretaceous, the land continued to drift into new shapes. Sea levels were much higher than today. Vast, shallow seas flooded the interiors of continents. In what is now North America, a great inland sea stretched from the Arctic Ocean down to the Gulf of Mexico. Warm waters covered low-lying regions across the globe. The climate was generally warmer, with little or no ice at the poles. This created long coastlines, shallow lagoons, coral reefs, and rich marine habitats. It was the perfect stage for giant sea reptiles to thrive. The oceans were full of life. Schools of fish flashed like silver arrows through the water. Ammonites with their coiled shells drifted in great numbers. Belemnites, squid-like creatures with internal shells, darted through the sea. Early sharks cruised silently, already perfect predators. Giant sea turtles paddled through warm currents. Above the surface, flying reptiles called pterosaurs swooped down to snatch fish. But beneath it all, hidden in deeper waters or lurking in ambush near the coasts, were the true rulers of the Cretaceous seas. One of the most fearsome of these rulers was Mosasaurus. This enormous marine reptile was not a dinosaur, even though it lived at the same time. Instead, it was more closely related to modern lizards and snakes. In fact, its name means Meuse lizard, because its fossils were first discovered near the Meuse River in Europe. When scientists first uncovered its giant skull in the late 18th century, they were shocked. Here was proof that an enormous reptile once swam in the sea, unlike anything alive today. Mosasaurus could grow to lengths of around 50 feet, and some of its relatives may have grown even larger. Its body was long and powerful, shaped like a giant muscular torpedo. It had a long tail with a fluke at the end, similar in shape to that of a shark, which helped it swim quickly. Its limbs had transformed into paddle-like flippers. Though it lived in the water, it still had to breathe air. Like whales today, it would have risen to the surface to take deep breaths before diving again. The head of Mosasaurus was enormous and terrifying. Its jaws were lined with sharp, conical teeth designed to grip slippery prey. It also had a special extra row of teeth on the roof of its mouth, which helped it hold on to struggling victims and swallow them whole. When Mosasaurus attacked, there was little chance of escape. Fossils show that it fed on fish, sharks, ammonites, sea turtles, seabirds, and even other marine reptiles. Some fossilized remains have been found with the bones of other mosasaurs inside them, suggesting that these giants sometimes attacked their own kind. Mosasaurus was not alone. It belonged to a larger group called mosasaurs, and during the Cretaceous they spread across oceans around the world. Some were smaller and more slender, perhaps feeding mainly on fish. Others were heavily built and powerful, capable of crushing hard shells. As the Cretaceous progressed, mosasaurs became more diverse and more dominant. By the later part of the period, they were among the top predators in the seas. Yet long before mosasaurs rose to full dominance, another group of marine reptiles had already been ruling the oceans for tens of millions of years. These were the plesiosaurs. Their body plan was very different from that of mosasaurs. Instead of a long, lizard-like shape, plesiosaurs had wide, rounded bodies with 4 strong flippers. They used these flippers almost like underwater wings, flying through the water in a smooth and graceful motion. There were 2 main types of plesiosaurs. Some had extremely long necks and relatively small heads. Others had shorter necks and larger heads. The long-necked forms are often the ones people imagine when they think of ancient sea monsters. Their necks could contain more than 70 vertebrae, making them flexible and surprisingly mobile. At the end of this long neck was a small head filled with sharp teeth. These plesiosaurs likely used their necks to sneak up on schools of fish, striking quickly before their prey could react. The short-necked plesiosaurs, sometimes called pleosaurs, were built for power. They had massive skulls and huge jaws capable of delivering crushing bites. Some plesiosaurs grew to lengths of more than 30 feet. Their teeth were thick and strong, perfect for seizing large prey. They may have hunted other marine reptiles, giant fish, and anything else they could overpower. In their time, they were among the most formidable hunters in the oceans. It is important to remember that both mosasaurs and plesiosaurs were reptiles, not fish and not mammals. They laid eggs on land or gave birth in the water, depending on the group. Evidence suggests that at least some plesiosaurs gave birth to live young in the sea, much like modern whales and dolphins. Fossils have been found showing a fully formed baby inside the body of an adult. This suggests that these reptiles were fully adapted to life in the ocean and did not need to return to land to lay eggs. The Cretaceous seas were not calm and empty places. They were crowded battlefields. Imagine swimming in warm, shallow water near a coral reef. Fish move in glittering schools. Suddenly the water around you grows darker as a shadow passes overhead. A massive shape glides silently below. Its flippers beat in steady rhythm. Its eyes scan for movement. A plesiosaur darts its long neck into a group of fish, snapping up several in a flash. Moments later, a larger predator appears, a mosasaur perhaps, drawn by the disturbance. The plesiosaur must flee or risk becoming prey itself. The ocean was a place where even top predators could be hunted. As the Cretaceous moved toward its later stages, mosasaurs became especially dominant. They seemed to replace some of the earlier large marine predators. Their bodies were more streamlined for fast swimming. Recent studies of their fossils show that their tails had crescent-shaped flukes, similar to those of sharks. This means they were powerful swimmers capable of bursts of speed. They could chase down fast prey in open water, making them even more formidable. The world's oceans at that time were also filled with other strange creatures. Giant ammonites with shells as wide as wagon wheels drifted in the currents. Some ammonites grew to more than 6 feet across. They were related to modern squids and octopuses, but carried heavy, coiled shells. Mosasaurs often fed on them, crushing their shells with strong jaws. Fossil evidence shows bite marks on ammonite shells that match the teeth of mosasaurs. Sharks were also evolving and diversifying during the Cretaceous. Though not yet as large as some of the famous sharks that would appear later in Earth's history, they were already skilled predators. In some places, sharks and mosasaurs may have competed for similar prey. Yet mosasaurs, being larger and more heavily built, may often have had the advantage. The seas were warm and rich in nutrients. High sea levels meant that shallow coastal waters spread across continents, creating broad continental shelves. These areas were full of life, as sunlight could reach the sea floor and support algae and plankton. Plankton fed small fish and invertebrates, which fed larger predators. At the top of this food chain swam the marine reptiles. It is fascinating to think about how these reptiles adapted to ocean life. Their ancestors once walked on land. Over millions of years, their bodies changed. Limbs became flippers, tails became powerful swimming tools, bones grew denser to help control buoyancy, nostrils shifted position on the skull, eyes grew large to see in dim underwater light. Their senses became tuned to movement and vibration in the water. Despite their fearsome appearance, these animals were not mindless monsters. They were living creatures shaped by evolution, perfectly suited to their environments. They hunted because they had to survive. They likely had complex behaviors. Some may have migrated with the seasons. Some may have cared for their young. We can only guess, but the evidence of live birth in plesiosaurs suggests a level of parental investment that may have been greater than once believed. The dominance of mosasaurs and plesiosaurs did not last forever. Toward the very end of the Cretaceous, disaster struck. A massive asteroid crashed into what is now the Yucatan Peninsula. The impact caused enormous explosions, earthquakes, and tsunamis. Dust and debris filled the atmosphere, blocking sunlight. Plants on land began to die. In the oceans, plankton populations collapsed. Without plankton, the entire marine food web began to fail. Large predators like Mosasaurus depended on abundant prey. When the base of the food chain disappeared, so did the creatures higher up. One by one, the great marine reptiles vanished. The same event that ended the age of the non-avian dinosaurs also wiped out mosasaurs, plesiosaurs, and many other marine species. The oceans would never be the same again. After their extinction, other groups rose to take their place. Sharks continued to evolve and grow larger. Millions of years later, marine mammals such as whales would return to the sea and become new giants of the oceans. Yet the reign of the marine reptiles during the Cretaceous remains one of the most dramatic chapters in the history of life. Today, we know about these ancient sea monsters because of fossils. Their bones are found in rocks that were once sea floors, in places that are now dry land, deserts, plains, even mountains. Scientists uncover skeletons of creatures that once swam in warm, shallow seas. Each fossil is a window into a lost world. A skull with sharp teeth tells of a predator's power. A long chain of neck bones reveals the strange design of a plesiosaur. A flipper bone shows how land animals transformed into masters of the ocean. When people first discovered plesiosaur fossils in the 19th century, some thought they resembled legendary sea serpents. Even today, stories of mysterious lake monsters are sometimes linked to the image of a long-necked plesiosaur. While these legends are not supported by scientific evidence, they show how deeply these ancient creatures have captured human imagination. Modern technology has allowed scientists to learn even more about these animals. By studying the microscopic structure of their bones, researchers can estimate how fast they grew and how warm their bodies were. Some evidence suggests that at least some marine reptiles may have had higher metabolisms than typical cold-blooded reptiles today. This would have allowed them to be active and powerful hunters in open water. Computer models help scientists understand how plesiosaurs swam using 4 flippers. Experiments suggest that they used a unique underwater flight style, similar in some ways to penguins. Mosasaurs, on the other hand, seem to have swum more like sharks, using powerful tail strokes for propulsion while steering with their flippers. The Cretaceous seas were not quiet. Waves crashed along long coastlines. Storms stirred shallow waters. Underwater volcanoes sometimes erupted, releasing heat and minerals. Coral reefs formed bright underwater cities filled with life. In deeper waters, sunlight faded into darkness. Even there, marine reptiles may have ventured, hunting in dim blue light. Imagine standing on the shore of a Cretaceous sea. The air is warm and humid. Strange plants line the coast. Flying reptiles circle overhead. In the distance, something breaks the surface of the water. A massive head rises, jaws opening to gulp air. For a moment you see rows of sharp teeth. Then the creature slips back beneath the waves, leaving only ripples behind. This was the world of Mosasaurus and the plesiosaurs, a world of giants, hunters, and constant struggle. Though they are long gone, their story reminds us how change shapes life on Earth. The seas that once belonged to reptiles now belong to mammals and fish. Continents have shifted, climates have cooled and warmed again. Yet the rocks still hold the memory of that ancient time when reptiles ruled the oceans. The monsters of the Cretaceous seas were not simply terrifying beasts. They were symbols of evolution's power to transform life. From small land-dwelling ancestors came streamlined ocean giants. From simple beginnings arose complex ecosystems filled with drama and danger. Their fossils speak of a time when the ocean depths hid creatures as impressive and awe-inspiring as any that walk the land. And when we look at their remains in museums today, we are reminded that Earth's story is far older and far more astonishing than we might imagine. Beneath calm modern seas lies the memory of an age when reptilian titans swam through warm waters, ruled by instinct and strength, in a world both beautiful and deadly. Early mammals did not begin as powerful rulers of the land. They began as small, cautious survivors in a world controlled by dinosaurs. For a very long stretch of Earth's history, these tiny creatures lived quietly beneath the feet of giant reptiles. They were not the main actors in their environment. Instead, they adapted, endured, and slowly changed in ways that would one day shape the future of life on Earth. The roots of mammals go back even further than the time of dinosaurs. Their ancestry can be traced to a group of ancient animals known as synapsids. These creatures first appeared more than 300 million years ago, long before the first true dinosaurs. Synapsids were not reptiles in the modern sense, even though many of them looked somewhat reptile-like. Over time, a special branch of these synapsids began to develop features that would later define mammals. These animals are often called therapsids. They showed gradual changes in their teeth, their jaw structure, and even their posture. One of the most important changes involved the jaw and the bones of the middle ear. Early synapsids had multiple bones in their lower jaw. As evolution continued, the jaw became simpler and stronger, with a single large bone forming the lower jaw. The smaller bones that once helped make up the jaw slowly shifted position and became part of the middle ear. This change greatly improved hearing. Modern mammals still carry this legacy, with 3 tiny bones in the middle ear that help transmit sound. This transformation did not happen suddenly. It took millions of years of slow and steady change. Teeth were another key development. Early mammal ancestors began to show differentiated teeth, meaning they had different shapes for different purposes. Instead of having rows of similar teeth like many reptiles, they developed incisors for cutting, canines for tearing, and molars for grinding. This allowed them to eat a wider variety of foods and process food more efficiently. Efficient chewing meant better digestion and more energy, which supported higher activity levels. By around 200 million years ago, during the late part of the Triassic period, the first true mammals began to appear. These early mammals were small. Most of them were no larger than a modern mouse. They lived during a time when dinosaurs were rising to dominance. The climate was often warm, and the continents were arranged very differently from today. The supercontinent Pangaea was breaking apart, creating new coastlines and environments. Living alongside dinosaurs was not easy. The large reptiles dominated most visible habitats. They were the main herbivores and the top predators. Early mammals could not compete with them in size or strength. Instead, mammals found a different strategy. They became small and often nocturnal. Being active at night helped them avoid many dinosaur predators that hunted during the day. The darkness became their ally. Nocturnal life shaped the evolution of early mammals in powerful ways. Their eyes became adapted for low light, and their sense of smell grew sharper. The development of whiskers, or vibrissae, helped them sense their surroundings in the dark. Their hearing improved as well, thanks in part to those specialized middle ear bones. The ability to detect tiny sounds in the night could mean the difference between life and death. Another defining feature of mammals began to appear during this time: fur. Hair provided insulation. Unlike reptiles, which rely heavily on external temperatures to control their body heat, mammals evolved a more constant internal temperature. This process is known as endothermy, or warm-bloodedness. Being warm-blooded allowed mammals to stay active in cooler conditions and during the night. However, maintaining a stable body temperature requires a lot of energy. This meant that early mammals needed efficient metabolisms and regular food supplies. Milk production was another revolutionary development. Female mammals evolved mammary glands that produced milk to feed their young. This provided newborns with rich nutrition and immune protection. Instead of laying eggs and leaving them to develop on their own, as many reptiles do, mammals invested more time and care into fewer offspring. Parental care became a central part of mammalian life. Protecting and nurturing young increased their chances of survival. Even though early mammals were small and hidden, they were not all identical. Over time, different groups began to branch off. By the time of the Jurassic period, around 170 million years ago, several distinct mammal lineages existed. Some resembled tiny shrew-like insect eaters. Others had adaptations for climbing or gliding. Fossils discovered in places like what is now China have revealed remarkably preserved specimens showing fur impressions and delicate skeletal details. One early mammal called Morganucodon lived roughly 200 million years ago. It had a mix of primitive and advanced features. Its jaw still showed some transitional characteristics, but it clearly belonged to the mammalian line. Another early form, Megazostrodon, also lived during the late Triassic and shows how these small creatures were already well adapted to insect-eating lifestyles. As the Jurassic period continued, mammals experimented with new ecological roles. Some species developed teeth suited for crushing hard-shelled insects. Others may have eaten small vertebrates or plant material. One fascinating fossil, Castorocauda, suggests that some early mammals were semi-aquatic. It had features similar to modern otters, including adaptations for swimming. This shows that even during the Age of Dinosaurs, mammals were exploring diverse ways of life. The Cretaceous period, which began about 145 million years ago and lasted until 66 million years ago, saw further diversification. Dinosaurs still ruled the land, but mammals continued evolving quietly. By this time, three major groups of mammals had emerged: monotremes, marsupials, and placentals. Monotremes, like the modern platypus and echidna, lay eggs. Marsupials give birth to very underdeveloped young that continue growing in a pouch. Placentals nourish their developing young inside the womb through a complex organ called the placenta. These reproductive strategies represent different solutions to the challenge of raising offspring. The placenta in particular allowed for longer development inside the mother's body, leading to more developed young at birth. This would later give placental mammals a major advantage after the extinction of the dinosaurs. Throughout the Age of Dinosaurs, mammals remained mostly small. There were a few exceptions, but generally they stayed under the size of a house cat. This small size was not a weakness. It was a strategy. Small bodies require less food. They allow animals to hide in burrows, under roots, and in thick vegetation. They can reproduce relatively quickly. These traits helped mammals survive in a dangerous world. The end of the Cretaceous period brought one of the most dramatic events in Earth's history. About 66 million years ago, a massive asteroid struck the region that is now the Yucatan Peninsula. This impact caused enormous environmental changes. Dust and debris filled the atmosphere. Sunlight was blocked. temperatures dropped, plants died and food chains collapsed. The non-avian dinosaurs, along with many other species, went extinct. Mammals survived this catastrophe. Their small size, flexible diets, and ability to live in burrows likely helped them endure the harsh conditions. After the dinosaurs disappeared, ecosystems were left with many empty niches. Mammals, which had spent millions of years evolving quietly, were ready to expand. In the millions of years that followed, mammals rapidly diversified. They grew larger. Some returned to the oceans and became whales. Others took to the skies as bats. Hoofed mammals spread across grasslands. Primates evolved in forests, eventually leading to humans. The quiet survivors of the dinosaur age became the dominant land animals. Yet even as mammals rose to prominence, they carried with them the legacy of their early history. Their fur, their warm blood, their complex teeth, their sensitive hearing, and their deep parental care all reflect adaptations forged in the shadows. The story of early mammals is a story of persistence. It is about finding opportunity in limitation. It is about thriving not through strength alone, but through flexibility and innovation. Fossil discoveries continue to add new details to this story. Advances in imaging technology allow scientists to examine tiny bones and even microscopic structures without damaging precious specimens. Each new fossil helps fill in gaps, revealing how gradual and intricate the transition from reptile-like ancestors to true mammals really was. The evolution of early mammals also reshaped ecosystems in subtle ways. As insect eaters, they helped control insect populations. As seed dispersers and occasional plant consumers, they influenced vegetation patterns. Their burrowing activities affected soil structure. Even in small numbers and sizes, they played meaningful ecological roles. Brain development was another significant trend. Early mammals had relatively larger brains compared to many reptiles of similar size. This supported improved sensory processing, learning, and memory. Living in complex environments, especially at night, required quick responses and adaptability. Over millions of years, this trend toward larger and more complex brains continued in certain lineages. The transformation from synapsid ancestors to early mammals demonstrates how evolution works through small changes over immense spans of time. No single generation suddenly became a mammal. Instead, tiny modifications accumulated. A slightly stronger jaw here, a slightly better hearing ability there, a small patch of insulating hair, a shift in reproductive strategy. Over countless generations, these changes added up. It is also important to recognize that early mammals did not evolve with a plan or goal. Evolution has no foresight. The traits that helped them survive in the dinosaur-dominated world were simply those that worked at the time. Their success after the extinction event was not guaranteed. It was the result of chance, resilience, and adaptability. Today, mammals are found on every continent and in nearly every environment. From polar regions to deserts, from mountain peaks to deep oceans, they have adapted in extraordinary ways. But all of this diversity traces back to those small, mostly nocturnal creatures that once scurried through the undergrowth while giant dinosaurs thundered overhead. The Earth has always been a restless planet, constantly reshaping itself through fire, pressure, and movement. Among the most dramatic forces driving these changes are supervolcanoes and intense geological activity, events that have left permanent marks on the planet's surface and influenced life in profound ways. These eruptions were not ordinary volcanic events. They were extraordinary explosions of energy, capable of transforming landscapes, climates, and ecosystems across entire continents. The effects of such geological forces reached far beyond the immediate surroundings, influencing the oceans, the atmosphere, and even the evolution of life itself. Volcanoes form where molten rock, known as magma, finds a path to the surface. In most cases, these eruptions are relatively small, sending lava flows, ash, and gas into the air. But supervolcanoes operate on an entirely different scale. Unlike typical volcanoes, which often build tall cones or mountains, supervolcanoes can create enormous depressions called calderas when their underground magma chambers collapse after massive eruptions. These calderas can stretch for tens of miles, leaving a sunken scar across the landscape. The volume of material ejected in a supervolcanic eruption can be thousands of times greater than that of a normal volcanic explosion, producing catastrophic consequences for the planet. One of the most well-known supervolcano systems exists beneath what is now Yellowstone National Park. Today, it is celebrated for its natural beauty, from colorful hot springs to powerful geysers, but in the past, it erupted with staggering force. Entire regions were buried under thick layers of volcanic ash, and the collapse of its magma chamber created a vast caldera. Events like these illustrate how supervolcanoes can reshape the Earth's surface, redirecting rivers, forming lakes and altering ecosystems over thousands of square miles. During periods of extreme geological activity, the Earth's crust experienced immense stress. Tectonic plates moved, collided and pulled apart, while mantle plumes, columns of extremely hot rock rising from deep within the Earth, thinned the crust and created new volcanic regions. Sometimes these forces combined to produce massive eruptions that covered entire landscapes with lava. Such events are known as large igneous provinces. In these cases, molten rock poured out of long cracks, spreading in successive layers for hundreds of thousands of years. Regions such as the Deccan Traps are testimony to this kind of geological fury, where vast plateaus of hardened basalt formed after repeated lava flows, altering the environment dramatically. Supervolcanic eruptions had consequences far beyond the immediate area. Ash and volcanic gases could enter the stratosphere and circulate around the globe, reducing sunlight and causing a temporary drop in temperature, sometimes referred to as a volcanic winter. Crops failed, forests struggled, and food chains were disrupted. At the same time, gases such as carbon dioxide and methane could linger in the atmosphere, leading to long-term warming once the ash settled. These extreme swings in climate placed enormous stress on plants, animals, and marine life. The oceans were particularly affected. Volcanic gases, especially carbon dioxide, dissolved in seawater, increasing acidity and reducing the availability of oxygen. Large regions of the oceans became inhospitable, creating conditions that could lead to mass die-offs. Acidification harmed creatures that relied on calcium carbonate to build shells, including plankton, corals, and mollusks. These changes at the base of the food chain had cascading effects, impacting fish, marine mammals, and even land species that depended on the ocean for sustenance. Supervolcanoes also reshaped the continents themselves. When magma chambers emptied, the ground above collapsed, forming calderas and creating new drainage patterns. Rivers and lakes changed course, valleys were flooded, and landscapes were transformed. Lava flows and pyroclastic deposits covered vast areas, and mud flows called lahars traveled for miles, destroying everything in their path. Even distant regions could be affected, as ash clouds spread thousands of miles from the eruption site. Volcanic eruptions were powerful drivers of evolution. The destruction they caused could wipe out species unable to adapt to rapidly changing conditions, while the survivors evolved in response to new challenges. Fertile soils formed from volcanic ash later supported dense vegetation, allowing life to recover and flourish. Volcanic landscapes created new habitats, and the redistribution of nutrients helped maintain the balance of ecosystems over long periods. While destructive, these forces were also essential to life's resilience. Geological activity during these periods also influenced the shape and movement of the continents. Mantle plumes sometimes lifted vast sections of crust, forming domes that eventually fractured to create rift valleys. Over millions of years, these rifts widened, filled with seawater, and became new oceans. Tectonic movements rearranged land and sea, altering climates, ocean currents, and rainfall patterns. This, in turn, determined where plants and animals could thrive, shaping the distribution of life across the planet. The visual and sensory impact of supervolcanic eruptions would have been overwhelming. Massive clouds of ash and gas darkened the sky, while lightning crackled within the eruption column. Explosions could be heard hundreds of miles away, and earthquakes caused by shifting magma shook the ground violently. Pyroclastic flows, carrying searing gas and volcanic fragments at hundreds of miles per hour, consumed everything in their path. The heat, force, and scale of these eruptions were almost impossible to comprehend. Supervolcanoes were not isolated events. They often occurred in regions of prolonged tectonic and volcanic activity. Mantle plumes continually supplied heat and magma, and repeated eruptions could occur over hundreds of thousands of years. Each eruption added layers of lava, ash, and gas to the landscape, gradually building large igneous provinces or enormous calderas. These events interacted with climate, ocean chemistry, and biological systems, creating feedback loops that could last for millions of years. Despite their destructive potential, supervolcanoes and intense geological activity contributed significantly to the planet's evolution. Volcanic gases were instrumental in forming the early atmosphere, supplying water vapor that condensed into oceans. Ash and lava provided nutrients for soils, encouraging plant growth once the immediate threat had passed. Volcanic landscapes created new ecological niches, enabling species to diversify and adapt. Even modern agriculture benefits from fertile volcanic soils formed during these ancient eruptions. Toward the end of the Age of Dinosaurs, Earth was shaken by one of the most powerful volcanic events in its entire history. In what is now the country of India, the ground split open again and again, releasing enormous amounts of lava, ash, and gas. This vast volcanic region is known today as the Deccan Traps. The word traps comes from a Swedish word meaning stairs, and that is exactly what the landscape looks like in many places. Huge step-like layers of hardened lava stacked on top of each other, stretching for hundreds of miles. The eruptions that formed the Deccan Traps did not happen in a single explosion. They unfolded over a long period of time, near the end of the Cretaceous period, roughly 66 million years ago. At that time, dinosaurs ruled the land. Giant marine reptiles swam in the oceans, and strange flying reptiles soared through the skies. Flowering plants had spread across continents, insects buzzed among them, and early mammals lived mostly in the shadows. It was a world that seemed stable and full of life. Yet beneath the surface, powerful forces were building. India was not always attached to Asia as it is today. Long ago, it was part of a southern supercontinent called Gondwana. Over millions of years, tectonic forces caused India to break away and drift northward across the ocean. By the time of the Deccan eruptions, India was an isolated landmass moving rapidly toward what would eventually become Asia. Deep below it, in the mantle of the earth, a plume of extremely hot rock may have been rising slowly upward. This plume, sometimes called the Réunion hotspot by modern geologists, is believed by many scientists to have played a major role in triggering the volcanic activity. Unlike a typical volcano such as those seen in places like Iceland or along the Pacific Ring of Fire, the Deccan eruptions were not mainly tall cone-shaped mountains exploding into the sky. Instead, they were mostly fissure eruptions. That means the lava did not always come from a single central crater. Instead, it poured out from long cracks in the ground. Imagine the Earth's crust splitting open like a wound, glowing rivers of molten rock spilling out and spreading across the land in vast sheets. The scale of these eruptions was almost beyond imagination. Scientists estimate that the total volume of lava released may have been more than 1 million cubic kilometers. That is enough molten rock to bury an entire country under layers of basalt, hundreds of meters thick. Today, the Deccan Traps cover an area of about 500,000 square kilometers, but they were once even larger. Erosion has worn them down over time, and parts have been buried or broken apart by later geological events. The lava that flowed from these fissures was mostly basalt, a dark, dense volcanic rock rich in iron and magnesium. When it first erupted, it would have been glowing bright orange and red, flowing like thick syrup across the landscape. Some flows may have traveled for dozens of kilometers before cooling and hardening. Over time, new flows covered older ones. Each eruption added another layer, building up the step-like structure we see today. But lava was not the only thing released. Along with molten rock came enormous amounts of volcanic gases. These gases included carbon dioxide, sulfur dioxide, water vapor, and other substances. Carbon dioxide is a greenhouse gas, which means it traps heat in the atmosphere. Sulfur dioxide can combine with water vapor to form tiny droplets of sulfuric acid, creating aerosols that reflect sunlight and cool the planet. The balance between these warming and cooling effects may have caused dramatic swings in climate. Some scientists believe that the Deccan eruptions played a major role in the mass extinction event that wiped out the dinosaurs and many other species. This extinction happened around 66 million years ago at the boundary between the Cretaceous and Paleogene periods. For many years, the main suspect was a massive asteroid impact in what is now the Yucatan Peninsula of Mexico, which created the Chicxulub crater. That impact released an enormous amount of energy, sending dust and debris high into the atmosphere and causing global darkness and cooling. However, the timing of the Deccan eruptions is very close to the time of this impact. Some studies suggest that the most intense phase of volcanic activity happened just before and just after the asteroid struck. This has led to debate among scientists. Did the asteroid alone cause the extinction? Did the volcanoes alone do it? Or did both events together push Earth's ecosystems beyond their limits? The volcanic gases released during the Deccan eruptions could have caused long-term climate changes. Large amounts of sulfur dioxide would have created short-term cooling episodes by blocking sunlight. Crops of microscopic plankton in the oceans, which form the base of marine food webs, may have struggled as sunlight decreased. On land, plants would have faced colder and darker conditions, affecting the herbivores that depended on them. At the same time, over longer periods, rising carbon dioxide levels could have led to global warming. These rapid shifts between cooling and warming would have placed extreme stress on living organisms. In addition to climate effects, volcanic eruptions can release toxic metals such as mercury into the environment. Scientists studying rock layers from the end of the Cretaceous have found spikes in mercury levels that match the timing of the Deccan eruptions. This suggests that volcanic emissions may have polluted air, water, and soil on a global scale. Such pollution could have harmed plants and animals directly, adding another layer of stress. It is important to understand that the Deccan eruptions were not a single moment in time. They likely occurred in pulses over several 100,000 years. Some pulses were more intense than others. During peak periods, lava may have poured out at astonishing rates, covering large areas in relatively short geological time spans. Between pulses, there may have been quieter periods when ecosystems had a chance to partially recover before being struck again. The landscape of India during this time would have been transformed again and again. Forests would have been burned or buried under lava. Rivers would have been blocked or redirected. Ash and gases would have filled the sky. Yet life is resilient. In areas not directly covered by lava, plants and animals may have survived, adapting to new conditions. The fossil record shows that some species disappeared gradually, while others vanished suddenly at the extinction boundary. The interaction between the Deccan eruptions and the asteroid impact is one of the most fascinating questions in Earth science. Some researchers suggest that the impact itself may have influenced the volcanoes. The shock waves from the asteroid striking Earth might have traveled through the planet's crust and mantle, possibly increasing the intensity of volcanic eruptions that were already underway. While this idea is still debated, it shows how connected Earth's systems can be. Today, the Deccan Traps are a striking feature of the Indian landscape. Cities such as Mumbai and Pune lie within or near this ancient volcanic province. The rich black soils in parts of the region, formed from weathered basalt, are excellent for agriculture. Farmers grow cotton, sugarcane, and other crops on land that was once covered by flowing lava. It is a powerful reminder that destruction in Earth's history often lays the foundation for future life and growth. The basalt layers of the Deccan Traps also preserve valuable information about Earth's past. Scientists study the chemical composition of the rocks to understand the source of the magma and the conditions deep within the mantle. By examining tiny crystals within the basalt, they can learn about temperatures and pressures at the time of eruption. Magnetic minerals in the rocks record the direction of Earth's magnetic field when the lava cooled, helping researchers track the movement of the Indian plate over time. When India eventually collided with Asia millions of years after the Deccan eruptions, the impact formed the Himalayan mountains. Thus, the same drifting landmass that once experienced massive volcanic outpourings later played a role in creating the highest mountain range on Earth. Earth's history is full of such connections, where events separated by millions of years are linked through tectonic motion. The idea that massive volcanic events can change global climate and cause extinctions is not unique to the Deccan Traps. Other large igneous provinces in Earth's history, such as those associated with the end Permian extinction, have also been linked to dramatic biological crises. These events remind us that life on Earth has faced extreme challenges before. In recent decades, advances in dating techniques have allowed scientists to measure the ages of volcanic rocks with greater precision. By analyzing isotopes of elements such as argon and uranium, researchers can determine when specific lava flows formed. These studies suggest that a large fraction of the Deccan lava was erupted in a relatively short time interval around the extinction boundary. This strengthens the argument that the volcanoes played at least some role in the environmental upheaval. Computer models of ancient climate have been used to simulate the effects of volcanic gas emissions. These models suggest that repeated pulses of sulfur-rich eruptions could have caused cycles of cooling lasting years to decades, followed by warming driven by accumulated carbon dioxide. Such unstable conditions would have been extremely difficult for large animals like non-avian dinosaurs to survive, especially if food supplies were disrupted. At the same time, smaller animals, including early mammals and birds, may have been better able to cope. Their smaller body sizes, flexible diets, and ability to shelter underground or in water may have given them an advantage. After the extinction event, these survivors diversified and eventually gave rise to many of the species we see today, including humans. The Deccan Traps eruptions stand as a powerful example of how geological processes can reshape the biosphere. They show that Earth is not a static world, but a dynamic planet with deep internal heat and moving plates. The ground beneath our feet has not always been stable. It has cracked open, poured out lava, and filled the air with gases capable of altering the global climate. Even now, hotspots and volcanic regions remind us that such forces still exist, though not currently on the same scale as the Deccan event. By studying the past, scientists hope to better understand how volcanic emissions affect climate systems. This knowledge can also inform our understanding of modern climate change, though the causes today are very different. The Deccan Traps are more than just ancient rocks. They are a record of a time when Earth's interior unleashed energy on a colossal scale. They may have helped bring an end to the Age of Dinosaurs, clearing the way for mammals to rise. They transformed landscapes, altered climates, and left a lasting mark that can still be seen today in the layered hills of Western India. However, the question of how much the Deccan eruptions contributed to the extinction remains an active area of research. Some scientists emphasize the dominant role of the asteroid impact, Others argue that long-term volcanic stress weakened ecosystems before the final blow. Many now believe that it was a combination of both events, working together in a deadly sequence. What is certain is that the Deccan Traps eruptions were among the largest volcanic events in Earth's history. Their scale, timing, and environmental effects make them central to understanding one of the most important turning points in the history of life. From fiery fissures in ancient India to the global extinction that reshaped life on Earth, the legacy of the Deccan Traps continues to shape scientific discovery and our understanding of the planet we call home. The end of the Cretaceous period was a time of unimaginable change on Earth, a moment when the world as it had been known for tens of millions of years seemed to come to a sudden and almost catastrophic halt. This was the period marked by the Great Mass Extinction event, an extraordinary episode in our planet's history when nearly 75% of all species vanished from the face of the Earth. The planet, which had been teeming with life of every imaginable form, from the smallest microscopic creatures in the oceans to the largest, most awe-inspiring dinosaurs roaming the land, experienced a level of devastation that changed the course of evolution forever. This extinction was not a slow fading away. It was sudden on a geological scale, striking with such force and speed that entire ecosystems collapsed, leaving behind a world that would take millions of years to recover and be reshaped entirely. The Cretaceous period, which stretched from about 145 million years ago to approximately 66 million years ago, had been a time of remarkable biological richness and diversity. Dinosaurs ruled the land with their impressive sizes, strange shapes, and cunning behaviors, while the oceans were filled with giant reptiles, early fish, and a variety of invertebrates. The skies were not empty either, for pterosaurs with their leathery wings and varied sizes soared above, hunting and gliding across vast landscapes. Flowering plants, or angiosperms, had flourished during this period, spreading vibrant colors and new sources of food for herbivorous creatures. Mammals, though present, remained relatively small and insignificant compared to the towering reptiles that dominated the planet. It was a time when life had reached heights of complexity, variety, and sheer spectacle that might have seemed permanent. Yet, beneath the surface of this thriving world, forces were gathering that would sweep away nearly everything so abruptly and ruthlessly that it still sparks fascination and debate among scientists today. The immediate cause of this mass extinction has long been the subject of careful study and sometimes heated debate. Today, most scientists agree that a cataclysmic event struck the Earth at the very end of the Cretaceous, a moment that left an indelible mark on the planet's geological and biological record. The strongest evidence points to the impact of a massive asteroid or comet, estimated to be about 10 to 15 kilometers in diameter, which collided with the Earth near what is now the Yucatan Peninsula in Mexico. This impact created what is known today as the Chicxulub crater, a colossal circular depression more than 180 kilometers across, whose formation released unimaginable amounts of energy. To put this into perspective, the force of the collision would have been millions of times more powerful than the largest nuclear bomb ever detonated by humans. The asteroid struck with such violence that it instantly vaporized rock, sending plumes of molten material, dust, and gas high into the atmosphere. The initial impact itself caused immediate devastation over thousands of kilometers, flattening forests, triggering massive earthquakes, and sending shockwaves across the oceans and continents. However, the asteroid's impact was only the beginning of a chain reaction that brought the mass extinction to its terrifying climax. The collision released enormous quantities of debris into the atmosphere, creating a thick, global cloud of dust and soot. This cloud blocked sunlight, plunging the Earth into what scientists call an impact winter, a dramatic cooling of the planet that lasted for months or even years. Without sunlight, photosynthesis, the process by which plants produce energy from light, would have been severely disrupted. Plant life, the foundation of nearly all ecosystems, began to collapse, Forests and flowering plants withered. Algae and phytoplankton in the oceans struggled to survive, and the entire food chain began to break down. Herbivorous dinosaurs and other plant-eating animals would have found themselves with rapidly dwindling sources of food, and soon carnivores that relied on them were also left without prey. The result was a cascading series of extinctions that reached into every corner of the planet, affecting creatures of all shapes and sizes, from tiny insects to massive dinosaurs. At the same time, the asteroid impact triggered global fires and volcanic activity that further intensified the crisis. Evidence suggests that the impact may have set off wildfires that swept across continents, burning vast areas of forest and releasing additional carbon dioxide and soot into the atmosphere. In some regions, volcanic eruptions were already underway, notably in what is now India, where the Deccan Traps, a massive series of volcanic lava flows, were spewing gases and lava over enormous areas. These eruptions, which had been occurring intermittently for thousands of years, contributed sulfur dioxide and carbon dioxide to the atmosphere, creating acid rain and further altering global climate patterns. The combination of asteroid impact, fires, and volcanic activity produced a perfect storm of environmental stresses, a lethal combination that few species could withstand. The consequences of this event were almost unimaginably vast. In the oceans, marine reptiles like mosasaurs and plesiosaurs disappeared entirely. Ammonites, which had thrived for millions of years and decorated the seas with their coiled shells, vanished completely. Many species of fish and invertebrates also faced extinction, and entire marine ecosystems collapsed. On land, the familiar giants such as Tyrannosaurus rex, Triceratops, Ankylosaurus, and Triceratops-like ceratopsians vanished without a trace. Smaller creatures such as early mammals, amphibians, and some birds survived, but the majority of large animals perished. Even insects, which are often highly resilient, suffered significant losses in diversity. Fossil records from this time show a sudden and sharp decline in species variety, a pattern that is visible in sediments deposited around the world at the boundary between the Cretaceous and the Paleogene periods, sometimes referred to as the Cape Each boundary. These sediments often contain high levels of iridium, a rare metal more common in asteroids than on Earth, which further supports the theory that a massive space object caused widespread destruction. One of the most remarkable aspects of this extinction is its suddenness. While some environmental changes may have been gradual, such as the volcanic activity in the Deccan Traps or shifts in sea levels and climate, the asteroid impact created a near instantaneous shock to the Earth's systems. In geological terms, instantaneous can still mean thousands of years, but compared to the slow evolutionary timescales of hundreds of thousands or millions of years, it was abrupt. Fossil evidence shows a stark boundary between life before the impact and life after, with a sharp reduction in both species and abundance. Imagine walking through a lush forest filled with enormous dinosaurs, flowering plants, and singing birds, only to witness that same forest reduced to a smoldering wasteland in a few short years. That is the scale of transformation the end Cretaceous extinction brought. The extinction also reshaped the trajectory of evolution in profound ways. With the disappearance of the dinosaurs and many other dominant groups, ecological niches that had been occupied for millions of years suddenly became empty. This created opportunities for surviving species to diversify and adapt to new roles in ecosystems. Mammals, once small and relatively inconspicuous, began to expand in size and variety, eventually giving rise to the rich diversity of forms seen in later periods, including the eventual evolution of primates and, ultimately, humans. Birds, many of which descended from small theropod dinosaurs, also radiated into new forms, becoming dominant in the skies in ways that had not been possible when giant pterosaurs were present. Even plants underwent significant changes, with flowering plants expanding further to fill ecological gaps left by the extinction of certain groups. In a sense, the mass extinction acted as a reset button for life on Earth, wiping the slate clean in some ways and allowing evolution to take entirely new directions. Scientists have learned much about this extinction by examining layers of rock, fossil records, and chemical signatures preserved in sediments. The thin layer of iridium-rich clay that marks the KPG boundary is found all over the world, from Europe to North America, South America to Asia, and even in parts of Antarctica. This global evidence indicates that the event was not local or regional, but a truly planetary catastrophe. Fossilized remains of dinosaurs and other extinct species abruptly stop appearing in layers above this boundary, while the appearance of new, smaller and more resilient species begins to increase in layers deposited after the event. These clues allow scientists to reconstruct a vivid picture of how life on Earth changed in a relatively short geological period. The ecological effects of the extinction were not limited to immediate loss of species. They also included long-term shifts in climate and geography. With the collapse of forests and reduction in photosynthesis, levels of oxygen and carbon dioxide in the atmosphere changed, contributing to further climate instability. Soil quality would have suffered from the loss of vegetation and microbial activity, affecting plant regrowth and the recovery of terrestrial ecosystems. In the oceans, the death of phytoplankton and other microscopic life disrupted the base of the marine food chain, causing ripple effects that lasted for thousands of years. Recovery was not immediate. It took millions of years for biodiversity to reach levels comparable to those before the extinction. Some groups, like mammals and birds, diversified rapidly, but others, like ammonites and marine reptiles, never returned. In this way, the end Cretaceous extinction did not just remove species, it permanently altered the course of life on Earth, favoring some lineages while closing the door on others forever. Interestingly, the extinction also affected the smaller and seemingly less significant forms of life, demonstrating that no species, regardless of size or adaptability, was completely immune. Tiny creatures like foraminifera, single-celled organisms with calcium carbonate shells that float in the oceans, suffered massive die-offs. Plants faced selective pressures, with some species surviving due to their ability to endure low light, harsh conditions, or poor soils, while others disappeared entirely. Insects, which often play crucial roles as pollinators and decomposers, faced similar pressures. This shows that the mass extinction was comprehensive, touching all levels of the food chain, from microscopic life to the largest land and marine animals. Even today, the legacy of this extinction is evident in modern ecosystems. The absence of dinosaurs created a world where mammals could become the dominant land animals, leading eventually to the rise of elephants, whales, and humans. Birds, which survived in smaller numbers, evolved into the vast diversity of species we see today, from tiny hummingbirds to massive flightless ostriches. Coral reefs, which had been dominated by different groups of organisms, slowly restructured themselves with new species filling niches left by extinct groups. In a sense, our world, the one that humans now inhabit, is a direct product of the end Cretaceous mass extinction. Had the asteroid never struck, it is conceivable that dinosaurs might still rule the land, mammals might have remained small and inconspicuous, and the evolutionary path that led to humans might never have occurred. Studying this event also provides crucial insights into the vulnerability of life on Earth to sudden, catastrophic changes. It reminds us that even dominant, widespread, and seemingly invincible species can vanish quickly under the right or wrong circumstances. It offers a humbling perspective on the fragility of ecosystems, the interconnectedness of life, and the potential consequences of rapid environmental change. For scientists, understanding the KPG extinction helps in interpreting patterns of resilience, adaptation, and vulnerability in life, which can inform conservation efforts today as humans face climate change, habitat loss, and other environmental pressures. While the asteroid impact remains the leading explanation, scientists also continue to study the interplay of other factors that may have contributed to the extinction, including volcanic eruptions, changes in sea levels, shifting climates, and ocean acidification. The end Cretaceous period was not just a moment of impact, but a complex interaction of multiple stresses acting on a finely balanced system. Each factor amplified the others, creating a catastrophic scenario in which the majority of species could not survive. It was, in essence, a planetary perfect storm of destruction.